You've probably seen the image. A heavy bowling ball gets placed on a stretched-out rubber sheet, and it creates this deep well. Then, someone rolls a little marble nearby, and it circles the drain, spiraling toward the bowling ball. This, we're told, is a picture of gravity. It's a simple, neat analogy that's been used for decades to explain one of the most fundamental forces of our universe. But what if I told you that analogy is broken? That it actually uses gravity to explain gravity, creating a circular argument that just doesn't hold up? Welcome to the science for deep sleep. If this kind of calm exploration into the universe helps you unwind, consider liking the video and subscribing to the channel. And wherever you are right now, whether near an ocean, a forest, a city, or somewhere quiet in between, feel free to share where you're watching or listening from. And what if the real reason you're stuck to your chair, the reason the Earth orbits the Sun, has less to do with the pull and much more to do with time itself? Tonight, we're going to take a slow journey. We're going to gently peel back the layers of our everyday understanding of gravity. The goal isn't just to learn new facts, but to change how we see the very fabric of reality. We'll start with the familiar idea of a simple pull, and we'll end by seeing the universe as a grand, silent, geometric dance. By the end, you'll see the cosmos, and your place in it, in a completely new light. So, take a deep breath, and let's begin. The world according to Newton. Gravity as a pull. For most of history, gravity was just a fact of life. Things fall down. An apple lets go of a branch and heads for the earth. It was just the way the world worked. It wasn't until the 17th century that Sir Isaac Newton gave us a language to describe this universal habit. He didn't just say things fall, he asked how they fall, searching for a rule that governed the apple, the moon, and everything in between. Newton's idea was both elegant and powerful, his law of universal gravitation. He proposed that every object with mass in the universe attracts every other object. It's an invisible, ever-present force, a pull. The strength of this pull depends on two things: how much stuff the objects have, their mass, and how far apart they are. The more massive the objects, the stronger the pull. The farther apart they are, the weaker it gets, and it weakens fast. If you double the distance between two objects, the force becomes 4 times weaker. Triple it, and it's 9 times weaker. This equation was revolutionary. Suddenly, the same force that made the apple fall was also keeping the moon locked in orbit around the Earth. The moon, in a way, is constantly falling toward us. But because it has so much sideways momentum, it continuously misses, caught in a perpetual dance of falling and flying. The Earth, in turn, is always falling toward the Sun, whose immense gravity holds our entire solar system together. Newton's law explained why planets move in predictable ellipses and even explained the tides, the rise and fall of our oceans as the gentle tug of the moon and the more distant pull of the Sun. Newton's vision is intuitive. It makes sense. We feel a pull. When you step on a scale, you're measuring the force of Earth's gravity pulling on your mass. We think of it as an invisible string, tying us to the ground. And for almost everything we do, this idea works perfectly. We still use Newtonian mechanics to send probes to other planets. It gives us the right answers. But Newton himself was troubled by a mystery at the heart of his own theory. He could describe what gravity did, but he couldn't explain how. How does this force travel across the empty vacuum of space? How does the Sun, 93 million miles away, know the Earth is there to pull on? And does it happen instantly? Newton's math implied that if the Sun were to vanish, the Earth would instantly fly off into the dark. This spooky action at a distance didn't sit right. Newton wisely made no guesses about the cause. He had found the rule, and for a while, that was enough. So for over 200 years, this was our universe, a clockwork system of objects pulling on each other with an invisible, instantaneous force. But as our measurements got more precise, tiny cracks began to appear in this perfect picture. The universe, it turned out, was a little stranger than a cosmic game of tug-of-war. The cracks in Newton's universe. For more than 2 centuries, Newton's law of gravity was king. But science is all about pushing theories to their limits to see where they break. And by the early 20th century, new discoveries were putting a lot of pressure on Newton's ideas, and small, persistent cracks started to show. The first problem was that nagging action at a distance. Physicists like James Clerk Maxwell had shown that forces like electricity and magnetism weren't instantaneous. They traveled as waves at the speed of light. If you jiggle an electron, the magnetic field doesn't change everywhere at once. A ripple of change moves outward. Why would gravity be any different? The idea of an instant force began to seem less like a mystery and more like a flaw. It broke a new, fundamental rule: nothing can travel faster than light. But the most famous piece of evidence against Newton came from our own solar system. It came from the planet Mercury. Astronomers had been tracking the planets for centuries, and Newton's laws predicted their paths with incredible accuracy. Almost. Mercury was the stubborn exception. Its orbit isn't a perfect, repeating ellipse. It slowly rotates over time. Imagine drawing an oval, and then slowly turning the paper it's on. That's what Mercury's orbit does in space. Now, some of this precession was expected. The gravitational tugs from other planets like Jupiter would naturally nudge Mercury's orbit. But after calculating all those effects, there was still a tiny bit of rotation left over. Mercury's orbit was precessing just a little bit faster than Newton's theory said it should. The difference was tiny, a mere 43 arcseconds per century. An arcsecond is 1/3600th of a degree. Yet, this tiny error was a huge problem. It was a constant whisper that something was missing. Scientists tried everything. Maybe there was an unseen planet, they called it Vulcan, orbiting even closer to the Sun. But no one ever found it. Maybe the Sun was slightly squashed. Maybe the law of gravity needed a small tweak. Nothing worked. The wobble in Mercury's orbit remained a stubborn, unsolved puzzle. These two issues, the infinite speed of gravity and the weird orbit of Mercury, set the stage for a revolution. The problem wasn't that Newton was wrong, exactly. His theory was just incomplete. It was an amazing approximation, but it was missing a deeper truth. The world was waiting for someone to see the problem in a completely new way. And that someone was a young clerk working in a patent office in Bern, Switzerland. Einstein's happiest thought: a new beginning. In 1905, Albert Einstein had already turned physics on its head with his theory of special relativity. It established that the speed of light is a universal speed limit, and as a result, space and time are not absolute. They're flexible, stretching and shrinking depending on how you're moving. But this new picture of the universe had a big hole in it. It didn't include gravity. Einstein spent the next decade wrestling with how to fit gravity into this new, relativistic world. The breakthrough came in 1907 with what he later called his happiest thought. It struck him while he was just sitting in his chair at the patent office. He imagined a person falling from a roof. As this person falls, they wouldn't feel their own weight. If they emptied their pockets, the objects would just float there beside them. In their immediate bubble, it would be as if gravity had simply vanished. Then, Einstein imagined that same person in a sealed, windowless elevator, far out in deep space. If the elevator is just floating, the person inside is weightless. But what if a cable started pulling the elevator up with a constant acceleration? The person would feel pressed to the floor. If they dropped an object, it would fall. From inside that box, there would be no experiment they could do to tell the difference between being accelerated in space and standing still on the surface of the Earth. This is the heart of his happiest thought, a concept we now call the asterisk equivalence principle asterisk. You can't tell the difference between being in a gravitational field and being in an accelerating frame of reference. They are two sides of the same coin. This simple idea has huge consequences. It means gravity might not be a force at all. Think about it. When you're standing on the ground, you feel the force of the floor pushing up on you, stopping you from falling. That's what you feel as weight. But what about the person in free fall? Newton would say gravity is still pulling them down. But Einstein's insight flips the script. The person in free fall is the one in a state of natural, unforced motion. They feel nothing. It's the person standing on the ground whose natural path is being interrupted by the upward push of the Earth. So, according to Einstein, falling is what happens when you are simply following the most natural, straightest possible path through the universe. But that leads to a huge question. If you are just moving in a straight line, why does your path curve toward the Earth? If there's no force, why do things fall? If falling objects are following straight lines, but those lines look curved to us, then it must not be the object's motion that's bent. It must be space and time itself. Welcome to spacetime, the fabric of reality. To really get Einstein's answer, we have to upgrade our mental picture of the universe. We tend to think of space as 3 dimensions: length, width, and height, where everything happens. And we think of time as a universal clock, ticking the same for everyone. Special relativity already showed this was wrong. Einstein had fused space and time together into a single, 4-dimensional continuum, spacetime. Now we can go back to that trampoline analogy. Let's look at it again. The idea is that a massive object like the sun, the bowling ball, curves the fabric of spacetime, the trampoline. A smaller object like the Earth, the marble, trying to travel in a straight line, finds its path bent by that curve. It follows the dip, and that's its orbit. This much is true to Einstein's idea. Mass tells spacetime how to curve. An object in motion just follows the straightest path it can through this curved landscape. We call that path a geodesic. There's no invisible pull. The Earth is just following the contours of spacetime that have been warped by the sun. An apple falls for the same reason. The apple isn't being pulled, it's simply following the straightest path available to it through the curved spacetime around the Earth, a path that happens to end at the ground. This simple phrase, mass tells spacetime how to curve, and curved spacetime tells matter how to move, is the soul of general relativity. It even explains why light bends. Light has no mass, so Newton's gravity shouldn't affect it. But in Einstein's picture, light has to travel through spacetime just like everything else. If spacetime is curved, the path of light has to follow that curve. In 1919, during a solar eclipse, astronomers photographed the stars near the sun. Just as Einstein predicted, their light was bent by the sun's warped spacetime, making the stars appear in the wrong place. It was a stunning confirmation. But this is where we have to stop and think, because the analogy starts to fall apart. What makes the bowling ball sink into the trampoline in the first place? Gravity. Earth's gravity pulls the bowling ball down. So the analogy uses the thing it's trying to explain. It's a circular argument. And why does the marble roll down into the well? Again, gravity. What does down even mean in space? There is no down. But the biggest failure of the trampoline analogy is that it only shows the curvature of space. It completely ignores the most important, most mind-bending part of the equation, the curvature of time. The real secret to gravity isn't how space bends. It's how massive objects distort the flow of time itself. The curvature of time, gravity's real secret. This is the part of our journey where we need to slow down, because this idea is one of the most profound in all of science. We've established that gravity isn't a force, it's the geometry of spacetime. But the engine of that geometry, the real secret of gravity, is something called gravitational time dilation. Einstein's theory predicts that mass doesn't just warp space, it warps time. Specifically, the stronger the gravity, the slower time passes. A clock at sea level, closer to the Earth's center of mass, will tick just a tiny bit slower than a clock on top of Mount Everest. A clock on the Sun would tick much slower than a clock on Earth. This isn't a mechanical trick, it's a fundamental feature of reality. Time itself flows at different rates in different places. We've measured this with incredible precision. The GPS in your phone relies on satellites orbiting the Earth. Those satellites are moving very fast, which slows their clocks down a bit, but they are also in a weaker gravitational field, which speeds their clocks up much more. The clocks on GPS satellites run faster than clocks on the ground by about 38 microseconds every single day. If scientists didn't correct for this warping of time, your GPS would be off by about 6 miles every day, making it useless in minutes. So every time you use a map on your phone, you're using proof that gravity warps time. But how does slowing time make an apple fall? Imagine you are always trying to move, straight ahead, through the 4 dimensions of spacetime. Now, think of an apple on a tree. The bottom of the apple is slightly closer to the Earth's center than the top. This means time is flowing just a tiny bit slower for the bottom of the apple than it is for the top. Let's try a different analogy. Picture 2 race cars side by side on a flat field, connected by a short axle. Their goal is to drive perfectly straight. As long as both wheels turn at the same speed, they will. But what if the left wheel is programmed to turn just a little bit slower than the right wheel? Even though both wheels are trying to go straight, the difference in their speeds will cause the whole thing to curve to the left. The path naturally bends toward the slower moving wheel. Now, replace the race cars with the top and bottom of the apple, and replace their speed across a field with their speed through time. The bottom wheel of the apple is moving through time more slowly than the top wheel. Because all the parts of the apple are connected, this difference in the flow of time forces its whole path through spacetime to curve. And the direction of that curve is downward, toward the source of the gravity, where time is flowing slowest. So, when the apple is released, it's not being pulled. It's just continuing on its straightest possible path through a spacetime where the time dimension itself is warped. Its fall is the inevitable result of it trying to go straight, where straight now points toward the ground. You, sitting in your chair, are experiencing the same thing. The lower part of your body is aging infinitesimally slower than the top of your head. Your natural path is to fall toward the center of the Earth. The only thing stopping you is the chair pushing up on you.
The force you feel isn't gravity pulling you down, it's the chair stopping you from taking your natural, straight-line journey through curved spacetime. This is the true revelation of general relativity. Gravity is just a side effect of warped time. If this idea of falling through time just clicked for you, or even if it just bent your brain in a new way, let me know in the comments. It's a concept that takes a while to sink in, and it's fascinating to hear how it lands with people. And if you enjoy these slow journeys into the biggest ideas in science, please consider subscribing to the channel. We have many more journeys to take together. Proof and consequences, seeing the curve. A theory this revolutionary needs proof. And in the century since Einstein published his equations, general relativity has passed every test we've thrown at it. We've already mentioned the first 2 big ones, the bending of starlight during the 1919 eclipse, which showed that space is warped by mass, and the daily miracle of GPS, which proves that time is warped by gravity. But what about that stubborn orbit of Mercury? When Einstein applied his new equations to the problem, they predicted an extra little bit of precession, on top of all the Newtonian effects. His math showed that Mercury's orbit should precess by an additional 43 arcseconds per century, the exact amount that had been baffling astronomers for decades. The mystery was solved. The curvature of spacetime was the missing piece. General relativity gets even stranger where gravity is very strong. Einstein's math suggested there could be objects so dense that they would curve spacetime infinitely, creating a region where nothing, not even light, can escape. We now call them black holes and today, we have overwhelming evidence for them. We've seen stars orbiting what looks like nothing at the center of our galaxy, their paths governed by a supermassive black hole. We have even taken a picture of a black hole's shadow, a direct visualization of spacetime warped to its breaking point. But maybe the most beautiful confirmation came in 2015. General relativity predicts that when huge objects accelerate, like two black holes spiraling into each other, they should create ripples in the fabric of spacetime itself. These gravitational waves would travel out at the speed of light. For decades, this was just a theory. The waves were thought to be too tiny to ever detect. Then, on September 14, 2015, the two detectors of the LIGO observatory felt a vibration. It was an impossibly tiny disturbance, a stretching and squeezing of spacetime 1,000 times smaller than an atom's nucleus. When translated into sound, the signal was a faint chirp. By analyzing it, scientists figured out its source: two massive black holes, 3 billion light-years away, that had finally collided and merged. For a split second, that collision released more energy as gravitational waves than all the stars in the observable universe combined. We didn't just see the event, we felt the fabric of the universe shake. It was the ultimate proof that spacetime isn't a static stage, but a dynamic, active part of the cosmic drama. The unfinished story and a sense of wonder. So, we've journeyed from a simple pull to a grand, four-dimensional spacetime. We've seen that gravity is not a force, but the shape of the universe itself. An apple falls not because the Earth pulls it, but because the Earth warps the time around it, and the apple is just following the straightest path through that warped geometry. We've seen the proof in bending starlight, in the orbit of Mercury, in our GPS, in the shadows of black holes, and in the tremors of gravitational waves. Einstein's vision of the universe has been proven right, again and again. And yet, the story isn't over. Science is never finished. As amazing as general relativity is, it describes the universe of the very large planets, stars, and galaxies. But we have another theory, quantum mechanics, that perfectly describes the universe of the very small atoms and particles. And here's the problem: the two theories don't work together. General relativity is a theory of smooth curves. Quantum mechanics is a theory of chunky, discrete packets of energy. When you try to use both at the same place, like the center of a black hole, the math breaks down into nonsense. But the universe is one single thing. It can't have two different sets of rules. So there must be a deeper theory, a theory of quantum gravity that unites them both. That's the next frontier. And so, as we end our slow exploration for tonight, we're left with a sense of profound wonder. We have replaced a simple idea with a much more complex one, but it is a complexity that reveals an incredible, underlying elegance. The universe isn't a collection of things pulling on each other, but a single, interwoven fabric of space and time, whose shape guides the destiny of everything inside it. The next time you feel your feet on the ground, perhaps you'll think of this. You're not being held down. You are a traveler on a curved path, riding the silent, invisible contours of spacetime. You are part of a cosmic dance governed by the geometry of existence itself. And in the quiet darkness, there is perhaps no thought more calming, no lullaby more profound, than that. Sweet dreams in a curved world. Part 2. Why space is not empty. When most people imagine space, they imagine absence. A giant black gap. A silent nothing stretched between stars. It feels natural to picture the universe that way, because from far away, that is what it seems to be. The stars shine. The planets glow faintly. And in between them, there appears to be only darkness. But appearances can be strangely misleading. Darkness is not the same thing as emptiness. And in the universe, that difference matters more than it first seems. If we follow the thread from where we left off, this becomes even more important. We ended with the idea that gravity may not be a simple pull in the old familiar sense. It may be something deeper, something tied to the very shape of reality. But the moment you hear that, another question quietly appears. What exactly is being shaped? If planets and stars are not just tugging on each other across a blank void, then what is this void really made of, if anything at all? What is space, before anything bends it? That question sounds simple, but it has a way of opening a very wide door. In ordinary life, we use the word empty very casually. An empty room, an empty glass, an empty road late at night. But none of those things are truly empty. The empty room is full of air, warmth, dust, sound, and the faint buzz of electronics. The empty glass is full of air and light. The empty road is full of heat shimmering off the asphalt, distant sound, drifting smells, and the movement of invisible radio signals passing overhead. What we usually mean by empty is simply this: empty of the things we immediately notice. And that turns out to be true in space as well. When you stand outside at night and look up, the darkness between the stars may seem blank. But that darkness is not blank. It is crossed by a light, bathed in radiation, threaded with magnetic fields, shaped by gravity, and governed by laws so consistent that the entire universe depends on them. Even what we call a vacuum, which sounds like the purest version of nothing, is not a perfect nothing at all. It is only a place with very little matter. That is a very different thing. This is one of the first mental shifts we have to make if we want to understand gravity in a deeper way. Space is not a passive backdrop. It is not just a container that holds planets the way a bowl holds fruit. It has properties. It has structure. It has behavior. It can stretch. It can curve. It can carry light. It can transmit waves. It can even, in a sense, remember the influence of mass. And once you see that, gravity starts to feel less like a mysterious force acting through nothing, and more like a consequence of living inside something. To feel how strange this is, it helps to go back to an older picture of the universe. For a long time, space was imagined as a kind of giant stage. Objects moved around on it, just as actors move around on a theater floor. The stage itself was not doing anything. It was simply there, fixed and silent, while matter did all the interesting work. That image is still hiding inside the way many of us think. We imagine the Earth floating in empty space, the Moon floating in empty space, the Sun floating in empty space. And it all sounds reasonable, until you start asking what floating really means. Floating through what? In everyday life, when something floats, it floats in water, or air, or some other medium. Even when something falls, it falls through air. But in the cosmic picture many of us inherited, planets float through nothing at all. They simply happen to be there. Then gravity is introduced as an invisible pull, and the mystery is pushed one step back instead of solved. We accept that something acts across emptiness, and because we are used to hearing it, it stops sounding strange. But it is strange. Imagine, for a moment, that you could somehow remove everything from a region of space. No dust, no gas, no stray atoms, no planets, no stars, no light passing through. We tend to assume that what remains would be absolute nothing. But physics does not really describe it that way. Even in that stripped-down case, there would still be distance. There would still be direction. There would still be the possibility for light to travel, for fields to exist, for time to pass differently under different conditions. There would still be the stage itself, except now we can no longer pretend the stage is simple. A useful way to think about this is to stop asking whether space contains anything, and start asking whether space can do anything. If the answer is yes, then space is not just nothing. And the answer is very clearly yes. Light moves through space. That may sound obvious, but it is already remarkable. Light does not need air to travel. It does not need a wire. It crosses the vacuum between the Sun and Earth in about 8 minutes, moving through what seems like emptiness. Yet it does so at a very precise speed, under very precise rules, in a way that is astonishingly reliable. That alone tells us something important. Space is not random blankness. It has consistent structure, consistent behavior. It allows some things and forbids others. The same is true of radio waves, X-rays, infrared radiation, and all the invisible forms of light that move around us all the time. Your phone works because signals pass through space. Your eyes work because light crosses space. Astronomers can study distant galaxies because ancient light has traveled through space for millions or even billions of years without losing the basic information it carries. A true nothing would not be so orderly. Then there are fields, which are easy to overlook because we do not see them directly. A field is, in simple terms, a way of describing how influence is spread through space. The Earth has a gravitational field. A magnet has a magnetic field. An electric charge has an electric field. These are not objects in the ordinary sense. You cannot hold a field in your hand like a stone, but the field changes what happens in the region around it. It gives space a kind of instruction. It tells matter and energy how to behave there. If you place a compass on a table, the needle turns. Not because a visible hand twists it, but because the magnetic field of the Earth is present in that region of space. If you toss a ball upward, it rises and falls in a very specific way because the Earth's gravitational field is present in that region of space. Even before we begin talking about curved space-time, this already hints at something profound. Different places in space are not identical. Space is not blank sameness. It has character, and that character can change from place to place. And once we begin to think this way, the night sky becomes much less empty. The darkness between Earth and the Moon is not nothing. It is a region filled with the Earth's gravitational influence, the Sun's light, the faint pull of the Moon, and the invisible geometry of spacetime itself. The darkness between stars is not nothing. It contains thin gas, dust, radiation, magnetic structures, and the wider gravitational influence of everything around it. Even the enormous spaces between galaxies are not perfect voids. They are crossed by light, shaped by cosmic expansion, and still connected to the larger structure of the universe. This is one reason astronomy can feel so humbling. The deeper we look, the more empty places turn out to be full of hidden activity. Even the vacuum itself, in modern physics, is not really understood as dead stillness. This is where the picture gets even stranger, though we can keep it gentle. In quantum physics, the vacuum is better thought of as the lowest energy state of a set of fields, not as the total absence of reality. That means even the quietest possible space is not exactly like a blank page. It is more like a page with very faint writing you can only notice under special light. It seems calm from a distance, but underneath that calm there is a kind of restlessness. Physicists have found subtle signs of this restlessness in experiments. They have measured tiny effects that suggest even near-empty space is not perfectly still. This does not mean space is full of obvious particles popping around like sparks in a fireplace. It means the vacuum has a hidden texture to it, a quiet instability, a background hum. Not chaos, exactly, but not emptiness either. And that should gently change the way we imagine the universe. The cosmos is not a set of islands sitting in a dead black sea. It is more like a vast, invisible fabric with matter woven into it. Some parts are dense and bright. Some parts are dark and thin. But none of it is truly cut off from the rest. If this slow journey through the hidden structure of the universe is helping you unwind, feel free to like the video, subscribe to the channel, and, if you want, leave a comment about where you're listening from tonight. It is always quietly amazing to imagine these ideas landing in so many different rooms, cities, and corners of the world, all at once. Now, there is another clue that space is not empty, and it may be one of the most beautiful. Space can expand. This is such a strange statement that it is easy to hear it without really letting it sink in. We often imagine galaxies racing away from each other through pre-existing emptiness, like sparks thrown outward from a firework. But on the largest scales, that is not quite the best picture. A more accurate one is that the space between galaxies is stretching. The universe is not only filled with objects moving through space. Space itself is changing. That idea is difficult at first because we are not used to thinking of space as something that can grow. A room does not quietly expand while you sleep. A road does not stretch beneath your car. But the universe is under no obligation to behave like our living room. On cosmic scales, the distance between distant galaxies increases because the geometry of the universe itself changes over time. The stage is not fixed. The stage can move. And if the stage can expand, then again, it is not nothing. This becomes even more powerful when we remember what we learned earlier. Space and time are not separate. They are woven together. So when we talk about space having structure, we are really beginning to talk about spacetime having structure. The distances between things, the paths objects follow, the rate at which clocks tick, these are all woven into one larger picture. This is why gravity became so much stranger after Einstein. Not because he made things more complicated for the sake of it, but because he realized the old empty stage picture was too thin to hold reality. There is a quiet kind of elegance in that realization. The universe does not need an invisible hand pulling planets around like beads on strings. It may only need a structured reality in which motion naturally follows shape. To make this less abstract, think about walking through a dark house you know very well. You may not be able to see every detail, but your body still responds to the layout. You turn because the hallway turns. You slow down near the stairs. You reach out where the doorway should be. The house guides your movement not by pulling you, but by being shaped the way it is. In a very loose and gentle sense, that is closer to what modern gravity is pointing toward. Space does not have to grab objects. Its structure can guide them. And structure is the opposite of emptiness. Perhaps the hardest thing here is that human vision keeps tricking us. We trust our eyes, and our eyes tell us that black means blank. But black only means that visible light is not reaching as strongly from that direction. It says very little about what is actually there. The deep ocean looks dark too, but darkness does not mean absence. It means depth, pressure, motion, life hidden from immediate sight. In a similar way, the blackness of space often hides activity rather than revealing a void. Even right now, as you sit listening to this, you are not sitting in emptiness. You are sitting in layers of invisible structure. Light is moving around you. Heat is moving around you. Radio signals are passing through the room. The Earth's gravity is holding you close. The Earth itself is spinning, orbiting the Sun. The Sun is moving through the galaxy. The galaxy is moving through a larger cosmic structure. And all of this is happening not inside a blank nothing, but inside a reality with rules, geometry, and hidden texture. It is almost dizzying to think about too quickly. But slowly, gently, it becomes calming. Because once you let go of the idea of a dead empty void, the universe starts to feel less like a lonely machine and more like a connected whole. The darkness between things is no longer an absence. It becomes part of the story. And this is why the question of empty space matters so much for gravity. If space were truly nothing, then gravity acting across it would always remain deeply mysterious. We could write equations for it, yes. We could measure it. We could predict it. But there would still be that uncomfortable feeling Newton himself carried, that sense of influence reaching across a blank gulf without any deeper explanation. But if space has properties, if space has geometry, if space is something more like a structured arena than an empty hole, then the mystery begins to shift. Gravity no longer has to be imagined as a magical pull across nothing. It can begin to look like a change in the structure that everything is already living inside. That is a much subtler picture, and in many ways a much more beautiful one. It means the sun does not need to reach out and drag the earth around. It means the earth does not need to cast some invisible rope that yanks an apple downward. Instead, matter and energy can shape the local structure of spacetime, and things moving through that structure follow the paths available to them. Not because they are being ordered around, but because that is what motion looks like inside a shaped world. In other words, gravity starts making more sense the moment space stops being empty. And perhaps that is the quiet lesson of this part. What looks like nothing often turns out to be something so subtle we almost miss it. The universe is filled with that kind of subtlety. The night sky looks still, but it is in motion. Space looks empty, but it is structured. Gravity feels like a pull, but it may be a path. Again and again, reality asks us to look past the first impression. The strange thing is, this does not make the universe colder. It makes it richer. The dark between stars is no longer wasted space. It is part of the architecture. The vacuum is no longer a blank. It is a quiet field of possibility. And your own life, lived here on this small planet, is not taking place in isolation. It is taking place inside that hidden architecture, inside a universe that is far more connected than it appears. So the next time you look up into that deep black sky, it may help to remember this. The darkness is not empty. It is simply subtle. It is full of rules, fields, light, and geometry too quiet for the eye to notice. And in a universe like that, gravity does not need to be a mysterious tug across a void. It can be something more intimate than that. Something built into the shape of the world itself. And that leads us naturally to the next step in our journey. If space is not empty, if it has structure, if it can carry light and hold fields and even stretch across cosmic time, then what happens when you place mass inside it? What does a planet do to the space around it? What does a star do? What does a black hole do? That is where things become even stranger. Because space is not just there. It can be changed. Part 3. How mass changes space. If space were truly empty in the simple everyday sense, then nothing placed inside it should change the space itself. A planet would just sit there, like a pebble resting in a vast black room. A star would glow, but the room around it would remain untouched. Matter would exist, and space would exist, but they would be separate things. One would be the object, the other would be the container. But the universe is quieter and stranger than that. The deeper picture is that mass does not merely occupy space. It changes the space around it. It alters the geometry of the region it lives in. It changes the shape of the paths that nearby objects can follow. And once that idea begins to settle in, gravity starts to look very different. Not like a hand reaching outward, but like the world around an object becoming subtly, and sometimes dramatically, different. That is the journey we are taking in this part. We are moving from the simple idea that space has structure to the deeper idea that mass can reshape that structure. And if that sounds abstract at first, that is all right. This is one of those ideas that does not usually arrive all at once. It softens into place. It becomes clearer the longer you sit with it. A helpful place to begin is with something very ordinary. Imagine walking through your home in the dark. You know where the walls are. You know where the furniture is. You do not need to see every detail for the room to guide your movement. The arrangement of the space is already doing that. A hallway channels you in one direction. A table forces you to turn. A staircase changes the way you move your body before you even think about it. The shape of the environment quietly tells motion what it can and cannot do. Now imagine that the house itself could change shape depending on what was inside it. Imagine that a heavy object in one room could subtly distort the hallway leading to it. Imagine that distances themselves could shift, angles could change, and paths that once looked straight might now bend slightly inward. That sounds impossible inside an ordinary house, of course. But on the scale of the universe, this is very close to what mass does to space. This is one of the great revolutions in how we understand reality. A planet is not simply a ball sitting in an unchanged arena. A star is not just a bright object hanging in darkness. Their mass changes the surrounding geometry. Their presence affects the very layout of the space around them. And that means gravity is not just about objects. It is also about the environment those objects create. For a long time, the older picture was enough. A force seemed to pull things together. The Earth pulled on the moon. The sun pulled on the Earth. The Earth pulled the apple from the branch. That description was extraordinarily useful, and in many everyday situations it still works beautifully. But it leaves a lingering discomfort. It tells us what happens, but not what the world must be like for that to happen so consistently. The modern picture offers something deeper. It says that mass changes the local rules of distance and motion. It does not merely sit in space. It shapes it. To understand that slowly, we can begin with a simple question. What does it mean for space to have geometry? In ordinary life, geometry feels fixed. A straight line is a straight line. Parallel lines stay parallel. The shortest distance between 2 points is simple and dependable. We learn these ideas so early that they become invisible. They feel less like ideas and more like facts built into reality. But that is only because most of the spaces we deal with are small and fairly flat. On a curved surface, things already become stranger. Imagine 2 people standing at the equator, both facing north. They begin walking in perfectly straight lines, as far as they can tell. At first, the paths seem parallel. But as they keep going, those paths slowly come closer together, and eventually they meet at the North Pole. Nothing about either person's motion had to become crooked from their own perspective. They each walked straight ahead. And yet the geometry of the surface caused their paths to converge. That is what curved geometry does. It changes what straight means. This matters because in the old everyday picture, space is treated as flat. But around mass, it may not be flat in that simple way. The presence of mass changes the geometry, which means that the paths followed by objects also change. And once again, the world begins to look less like a tug of war and more like motion unfolding inside a shaped landscape. It is very tempting here to reach for the familiar rubber sheet analogy, because it has helped many people get their first feeling for this idea. A heavy object placed on a stretched sheet creates a dip, and smaller objects roll toward it. There is something useful in that image, but only if we use it gently. It gives a feeling for the way a heavy object can affect the surrounding environment. But it also has limits. It uses gravity to explain gravity, and it can make it seem as though the whole story is just about things rolling downhill in ordinary space. The real picture is deeper than that, and quieter too. What matters most is not the literal image of a sheet, but the principle hiding inside it. Mass changes the region around it. It gives nearby motion a new shape to respond to. That is the heart of it. Think of the Earth. In the old picture, the Earth sends out a gravitational pull that reaches an apple and drags it downward. In the newer picture, the Earth's mass changes the structure of the spacetime around it, and the apple moves in response to that shaped structure. The difference may sound small when phrased casually, but it changes the meaning completely. One picture imagines a pull across emptiness. The other imagines a change in the world's geometry. The apple is not being singled out by some mysterious long-distance command. It is simply moving through the kind of space that exists around a planet like Earth. The same goes for the moon. The moon is not hooked to Earth by an invisible rope. It is moving through the shaped region Earth helps create. And Earth, in turn, is moving through the shaped region created by the Sun. What we call an orbit is not just one object endlessly chasing another. It is a pattern of motion inside curved geometry. This is why mass matters so much. More mass means a greater change in the surrounding structure. A small asteroid affects the nearby geometry only a little. A planet affects it more. A star much more. A neutron star or black hole, more than almost anything else we know. Mass is not just more stuff. In this deeper picture, more mass means a stronger reshaping of spacetime. That reshaping does not have to be thought of as visible or dramatic. Most of the time it is subtle. You cannot stand in a field and see the geometry of the Earth curving around you with your eyes, but you experience its consequences constantly. You feel weight. You see things fall. You watch the moon keep its place in the sky month after month. You notice that tides rise and fall in patient rhythm. All of these are signs that mass has changed the structure of the region we live inside. And this is where something beautiful begins to happen. Gravity becomes less like a separate force added on top of reality, and more like a natural expression of reality's shape. A good way to feel this more intuitively is to think about paths. Imagine rain falling on a wide landscape at night. The droplets do not need a map. They do not need instructions. They simply follow the shape of the ground. If the ground is flat, they spread one way. If there is a shallow valley, they gather there. If the terrain curves, their paths curve with it. The rain does not have to be told where to go by a distant hand. The landscape already answers that question. In a very broad and careful sense, matter moving near mass is like that. Objects follow the available paths of the geometry around them. And when the geometry changes, the paths change. What makes this especially powerful is that it explains why different objects, regardless of what they are made of, often fall in the same way. A rock falls. A piece of metal falls. A book falls. They are different materials, different colors, different textures. Yet in the absence of air resistance, they respond in the same way to gravity. That was always a little mysterious in the old force picture. Why should everything respond so uniformly? In the geometric picture, the answer is gentler. They are not being grabbed differently according to their substance. They are simply moving within the same local structure. The space around Earth has a certain geometry, and many things near Earth follow that geometry in nearly the same way. This is one reason astronauts in orbit experience weightlessness. It is very easy to imagine they have escaped gravity, but that is not really true. Earth's gravity is still strong where many satellites orbit. The astronauts are not beyond gravity. They are in continuous free fall, moving through the shaped region around Earth in a way that causes them to keep missing the ground. Their spacecraft, and their own bodies, are following that path together. There is no floor pushing up on them as there is here on Earth, so they feel weightless. That detail is quietly important. Weight is not simply the same thing as gravity. Much of what we call feeling our weight is actually the experience of the ground preventing us from following the path we otherwise would. The floor interrupts the motion that the shaped geometry would allow. It pushes back. And that push is part of what we feel. That is a strange thought to bring into a quiet night, but it can also be calming. You are not being pinned to the Earth by some crude invisible hook. You are living in a place where mass has shaped the structure of reality, and your body responds to that structure every moment. The Earth does something else too. It changes not only how things move, but how nearby distances and durations are best understood. We will go much deeper into time later, because time is where the picture becomes truly mind-bending. But even here, we can begin to sense that the change caused by mass is not just about space in a narrow sense. It is about spacetime. The Earth does not merely create a special region in space. It changes the local fabric in which both distance and time are woven together. That is why Einstein's picture ended up being more than a refinement of Newton. It was a different way of imagining reality itself. And it solved problems the older picture struggled with. One famous example was Mercury. Mercury's orbit did not behave exactly as Newton's equations predicted. It was close, very close, but not perfect. There was a tiny extra shift in the orbit that the old force picture could not fully explain. It was a small discrepancy, but in science, small discrepancies matter. They are often where deeper truths begin to show themselves. Einstein's theory accounted for it. The mass of the Sun was not merely pulling on Mercury across empty space. The Sun was reshaping the spacetime around it, and Mercury's orbit made more sense once that geometry was included. The path Mercury followed was not just the result of a force. It was the result of moving through a region whose structure had been changed by the Sun's mass. That small success mattered because it suggested the new picture was not just poetic. It was accurate. And once that door opened, more followed. Light itself could bend near massive objects. That is astonishing, because light has no rest mass in the ordinary sense, and yet it still follows the geometry of spacetime. If a star or galaxy changes the structure around it, light passing through that region can take a slightly curved path. We have observed this. Distant galaxies can appear stretched, doubled, or distorted because their light has traveled through the shaped geometry around other massive objects on the way to us. The universe itself can behave like a lens. That only makes sense if mass changes the world around it. By this point, the older image of space as passive emptiness starts to fade. Space is not merely there. It participates. And matter is not merely stored inside it. Matter helps write the local shape of reality. There is something deeply restful in that, once the initial strangeness passes. It means the universe is not a set of disconnected objects bumping through a dead void. It is more relational than that. Objects matter because of how they shape the wider world around them. And the wider world matters because it shapes how objects move within it. Everything is bound together not by a crude mechanism, but by shared geometry. If this kind of slow, quiet science helps you settle your thoughts for the night, you can gently support the channel with a like, a subscription, or a comment about what part of the world you're listening from. It is always a strangely comforting thought that so many minds can be following the same invisible ideas under different skies. There is another reason this picture matters, and it may be the most human one. It changes the way we imagine being small. In the old picture, small objects seemed almost helpless. Forces reached out and acted on them. But in the geometric picture, even the smallest object is still part of the same grand order. A leaf falling from a tree, a satellite circling Earth, a planet circling the Sun, a star moving through the galaxy. All of them are participating in the same shaped reality. They are not random things being shoved around. They are tracing paths through an ordered cosmos. That does not make the universe less mysterious. It makes it more coherent. And coherence matters, especially at night, when big ideas can easily become cold if we hold them too rigidly. The universe, as strange as it is not chaos stitched together. It has quiet consistency. Mass changes space. Changed space guides motion. Larger masses produce deeper changes. Smaller masses respond within those changes. Again and again, the same pattern appears. A star lives inside the geometry shaped by a galaxy. A planet lives inside the geometry shaped by a star. A moon lives inside the geometry shaped by a planet. Even we, sitting on Earth, live inside layers of these influences at once. The local and the cosmic are not separate worlds. They overlap. And yet, most of this happens invisibly. That may be the strangest part. Reality is full of hidden architecture. You do not wake each morning and see spacetime bending outside your window. You see sunlight, buildings, clouds, perhaps trees moving in the wind. But underneath those ordinary things is a deeper order. The earth beneath your feet is not just beneath you. It is shaping the region you live in. The sun overhead is not merely shining. It is helping determine the geometry in which the whole solar system moves. This is one reason science can feel almost like learning to see with a second set of eyes. The first set sees surfaces, colors, motion, and ordinary objects. The second begins to notice structure, pattern, field, geometry, and invisible order. Neither is false. But the second gives the first a much deeper meaning. And it prepares us for what comes next. Because once we accept that mass changes space, another question naturally appears. If mass reshapes the region around it, then what does motion inside that region actually look like? Why does an orbit happen instead of a fall straight inward? Why does a falling object accelerate? Why does the moon keep missing Earth? Why does the Earth keep missing the sun? In other words, how does a shaped space produce the movements we actually observe? That is the next step. For now, it is enough to rest with this. Space is not empty. Mass is not passive. The world around a planet or star is not the same as the world far from such things. The presence of mass changes the local architecture of reality, and what we call gravity begins there. Not as a grab, not as an invisible rope, but as the quiet fact that the universe around matter is no longer flat and simple. It has been changed, and everything nearby must move accordingly. Part 4: Why Objects Fall Without Being Pulled. By this point in our journey, the picture of gravity is already beginning to change. We started with the familiar feeling that gravity is a pull, a force, an invisible hand reaching across space to bring things together. Then, slowly, that image began to soften. Space stopped looking empty. Mass stopped looking passive. And the world around planets and stars began to look less like a blank stage and more like a shaped environment, a structure with its own quiet rules. But now we arrive at the part that often feels the strangest the first time you hear it. What if objects do not fall because they are being pulled at all? What if an apple drops from a branch, not because the earth reaches out and drags it downward, but because falling is simply what motion looks like in the kind of world the earth creates around itself? That idea has a way of sounding almost impossible at first. After all, when something falls, it certainly feels like it is being pulled. The sensation is immediate and familiar. A dropped glass hits the floor. Rain falls from clouds. A rock sinks down a hillside. A child jumping from a chair lands back on the ground. Everything in daily life seems to confirm the same simple truth. Things go down because gravity pulls them down. And yet the deeper picture asks us to look again, a little more carefully. Sometimes the universe reveals its strangest ideas through a very small shift in perspective. Not by changing the facts, but by asking us to notice the same facts from a new angle. And this is one of those moments. Let us begin with something very ordinary. Imagine you are standing still in a room. Your feet press against the floor. You feel your body held in place. This sensation is so normal that it barely draws attention. It seems obvious that gravity is pulling you downward and the floor is simply stopping you from sinking through it. But now imagine a different situation. Imagine stepping off a ledge, just for an instant, like missing a stair in the dark. There is that brief, unmistakable sensation in the body. A sudden lightness. A small lurch in the stomach. For a split second, something changes. And if the fall were long enough, as in a skydiver's jump or an astronaut's orbit, that sensation of weight can fade into something closer to floating. That is already a clue. Because if gravity were simply a pull in the same sense as a rope or a magnet, then falling should feel like being yanked. It should feel like some external grip taking hold of you and dragging you downward. But that is not what free fall feels like. In fact, free fall feels strangely like the opposite. It feels like release. This was one of Einstein's deepest insights, and it began with a surprisingly simple thought. He realized that a person falling freely does not feel their own weight. If you are in a freely falling elevator, and you let go of an object from your hand, it does not crash to the floor in the usual way. It floats beside you. For that brief moment, the usual force of weight seems to vanish. That observation is much stranger than it first appears. Because if falling feels like weightlessness, then perhaps the usual state of being pressed against the ground is not the natural one after all. Perhaps the natural motion is the falling itself, and what feels like force is actually the interruption of that motion. This is the quiet reversal at the center of the modern view of gravity. It suggests that when an apple falls from a tree, it is not being forced into some unnatural path by a distant pull. Instead, it may simply be following the most natural path available to it in the curved spacetime around Earth. The force-like feeling enters the story only when that path is blocked, when the ground gets in the way. That is not the way most of us first learn it, so it takes a little time to settle. A gentle way to think about it is this. In ordinary life, we often assume that staying still is the natural state, and falling is what needs explaining. But in the deeper picture, it may be almost the other way around. The apple hanging on the branch is the unusual case. The branch is preventing it from doing what the local geometry would otherwise allow. When the stem finally gives way, the apple is released into the path spacetime has already laid out for it. That path happens to lead toward the ground. And this is why the word straight becomes so important, even though it sounds misleading at first. In everyday flat space, a straight path is exactly what it sounds like. A ruler line, a beam of light across an empty room. But in curved spacetime, the straightest possible path may not look straight in the old familiar way. It may curve when viewed from within ordinary space, because the geometry itself is no longer flat. This is where gravity stops being a tug and starts being a path. Imagine you are on a vast curved landscape covered in fog. You cannot see the whole terrain. You can only see what is immediately around you. You start walking in the straightest direction you can manage, never deliberately turning left or right. From your own perspective, you are just moving straight ahead. But if someone high above could see the whole landscape, they might notice your path bending gently because the ground itself is curved. You are not turning because of a pull. You are turning because straight ahead means something different on a curved surface. That is closer to what the modern view of falling suggests. An apple released from a branch is not deciding to dive toward Earth. It is not being selected by a force in the crude everyday sense. It is simply following the straightest available path through a region of spacetime that has been shaped by Earth's mass. That path, when translated into our everyday language, looks like a fall. This is one of those ideas that becomes calmer the longer you stay with it. At first it sounds almost too strange to use. But then something shifts. The old questions begin to loosen. How does the Earth reach the apple? Why does the pull act through emptiness? What carries the force? Those questions do not vanish completely, but they change shape. Because the apple is no longer being acted on across a void. It is moving within a local structure that already contains the answer. And that local structure does not need to send instructions in the old way. It simply has a geometry, a shape, a set of natural paths. This also helps explain why everything falls in such a similar way. A stone, a coin, a book, a piece of fruit, even a feather if air resistance were removed, all respond similarly in a gravitational field. That old fact puzzled people for centuries, because it hinted that gravity was not behaving like most other forces. A heavy object and a light object fall in the same way when air is not involved. Why should they? If force is equal to mass times acceleration, why should different masses share the same acceleration? The geometric picture gives a gentler answer. These objects are not being dragged differently according to what they are made of. They are all following the same local structure of spacetime. Their internal differences matter much less than the environment they share. The region around Earth presents certain natural paths, and many objects near Earth move along those paths in nearly identical ways. That is why gravity is so universal. It does not care much about color, chemistry, or texture. It is not selective in the way magnetism or electricity can be. It is about the shape of the world nearby, not the material identity of the falling object. This is also why an orbit can be understood as a kind of continuous fall. The moon is falling toward Earth, but it has enough sideways motion that it keeps missing. The Earth is falling toward the sun, but it keeps missing as well. That old phrase from Newton's era remains surprisingly useful, though it now sits inside a deeper framework. To orbit is, in a sense, to keep following the straightest available path through curved spacetime while never crashing directly inward. It is a beautiful picture once it becomes familiar. A planet is not being whipped around the sun like a stone on a string. It is moving freely, faithfully, through the geometry created by the sun's mass. Its path closes into an orbit because that is what the local shape of spacetime makes possible. Free motion, not forced motion, becomes the key. And this is why astronauts feel weightless while orbiting Earth. Not because gravity has disappeared, but because they are in free fall. Their spacecraft and their bodies are all following the same curved path together. Nothing inside the spacecraft needs to press upward on them to interrupt that path, so they float. It is the floating, not the standing, that is closer to unforced motion. The floor beneath your feet, by contrast, is constantly interrupting the path you would otherwise follow. That is what your weight really is in this deeper view. It is not simply gravity pulling on you. It is the floor pushing back against your natural path through curved spacetime. The chair beneath you is doing the same. It prevents you from continuing along the route the local geometry would offer if nothing blocked it. The pressure you feel is the pressure of being held off that path. There is something wonderfully strange about that. It means that sitting still in a chair is not as simple as it feels. It is not just rest. It is, in a certain sense, a constant refusal of free fall. The chair pushes upward. The floor pushes upward. The ground itself prevents the motion that Earth's own curved spacetime invites. So the thing you usually call gravity in your body is partly the experience of resistance. You can feel the elegance of this by thinking about a person in deep space inside a rocket. Imagine the rocket far from planets, far from stars, in a region where gravity is very weak. If the rocket drifts calmly, everything inside floats. A dropped object stays near you. You feel weightless. But now imagine the rocket engines switch on and begin accelerating steadily. Instantly, the floor presses into your feet. A dropped object falls to the floor. It begins to feel, inside that rocket, almost exactly like standing on Earth. This is not just a clever science fiction idea. It was one of Einstein's great clues. He realized that locally, for a person inside such a sealed room, there may be no easy way to tell the difference between being in a gravitational field and being accelerated. A room on Earth and a rocket accelerating through deep space can feel the same. The pressure in the feet, the falling of objects, the sensation of weight, all can match. That tells us something profound. It suggests gravity may not be a force in the ordinary sense at all. It may instead be deeply tied to acceleration, geometry, and the local structure of spacetime. This idea became known as the equivalence principle, but the name matters less than the feeling behind it. The feeling is this: being supported on the ground and being accelerated upward may belong to the same deeper story. And once you begin to think in that way, the old tug-of-war picture starts to fade. In its place, a new one appears. Objects do not need to be yanked into motion. They may simply follow natural paths, while what we call weight comes from being prevented from doing so. This shift also changes the emotional texture of gravity. It makes the universe feel less mechanical and more architectural. Less like a system of invisible strings, more like a world of shaped possibilities. Think about a marble placed inside a gently carved wooden groove. If released, the marble rolls along the groove. We do not need to say the wood is pulling it sideways in any mystical sense. The shape of the surface already explains the route. Or think of water finding the contours of a riverbed. The water is not commanded by the riverbed. It simply responds to the structure present there. Again, these are imperfect analogies, because in the real universe we are talking about spacetime rather than grooves and riverbanks. But they help the intuition. They remind us that motion can be guided by shape, not only by direct push or pull. This matters because it restores a kind of quiet dignity to falling. An object in free fall is not being bullied by the universe. It is, in a sense, moving naturally, freely, faithfully. It is the object supported against free fall that is experiencing the interruption. And that means the ground under your feet is not just a passive platform. It is an active participant. It prevents your natural path. It presses on you. It keeps you from moving the way spacetime around Earth would otherwise let you move. There is a subtle comfort in this, especially at night when ideas can become too sharp if handled carelessly. The universe is not a collection of things randomly dragged around by hidden forces. It is more orderly than that, more coherent. Objects move as they do because the world around them has shape, because mass changes geometry, because geometry gives rise to paths, because paths, when followed, become what we call motion. And falling is one of the simplest examples of that. If this slow unfolding of the universe is helping you settle in for the night, feel free to gently support the channel with a like or a quiet subscription. And if you want, you can leave a comment sharing where in the world you're listening from tonight. There is something peaceful about imagining all of us, under different skies, thinking about the same invisible structure that holds our worlds together. There is another clue that falling is not just a pull, and it comes from light itself. Light does not have rest mass the way ordinary objects do, and yet light also responds to gravity. It bends when passing near massive objects. It follows the structure of spacetime too. This is one of the most astonishing confirmations of the geometric picture. If gravity were simply a conventional pulling force acting only on massive objects, the behavior of light would be hard to understand in the same framework. But if mass changes the local geometry, then light also has to move through that changed geometry. It follows the available paths, and those paths can bend. That is why starlight passing near the sun can be deflected. That is why massive galaxies can distort the appearance of more distant ones. Gravity is not merely about heavy things falling. It is about the local shape of reality affecting motion itself, even the motion of light. And if light follows the geometry, then the picture becomes even more unified. Matter follows it. Planets follow it. Moons follow it. Light follows it. In each case, what we observe as gravitational behavior arises because mass has changed the structure nearby. This is one reason Einstein's view felt so powerful once the evidence began to support it. It was not just another force law. It was a redesign of the whole picture. Instead of adding another invisible interaction to the list, it said that gravity is woven into the very framework in which everything else moves. That kind of explanation has a different flavor. It feels less like patching a machine and more like uncovering a hidden pattern. Of course, even with all of this, the old language of pulling does not disappear entirely from ordinary life. It remains useful. If you say the earth pulls an apple down, people understand you, and for many practical purposes it works. But underneath that familiar language there is a richer story waiting. A calmer one, perhaps. A story in which the apple is not a victim of a distant force, but a traveler following a path laid out by the geometry of the world. And once you let that settle, everyday life acquires a certain hidden depth. A dropped spoon in the kitchen is not merely falling. Rain sliding down a window is not merely falling. A diver cutting into water, a satellite circling overhead, a comet sweeping close to the sun, all are tracing paths within shaped spacetime. The same deep principle moves quietly through the ordinary and the cosmic alike. That is one of the loveliest things about science when it is given time to breathe. It does not only tell us exotic things about black holes and distant galaxies. It also changes the meaning of the simplest events. An apple falling, a foot touching ground, a cup slipping from a hand. Underneath these familiar moments is a structure vast enough to hold planets and stars, and yet intimate enough to touch the movement of a single leaf. And we are inside that structure too. You are inside it right now, listening to these words. Your body rests against a chair or a bed or the floor. The earth beneath you shapes the nearby spacetime. The sun shapes the wider region through which Earth moves. The galaxy shapes a larger region still. Layer upon layer, the universe provides the architecture within which your own stillness, your own breathing, your own heartbeat take place. That does not make you small in an empty way. It makes you local to something immense. It means your life unfolds not in a meaningless void, but within a world whose hidden order is both subtle and astonishingly consistent. The same principle that guides planets also touches your body. The same geometry that bends starlight also explains why your feet meet the ground. And that brings us to the edge of the next question. If objects are not falling because they are being pulled, in the old crude sense, then why do orbits remain stable? Why does Earth not simply spiral into the Sun? Why does the Moon not crash into Earth? What exactly determines the graceful paths bodies follow when moving through curved spacetime? That is the next part of our journey. Because once falling becomes a path, orbit becomes a kind of dance. And that dance is one of the most beautiful things in the universe. Part 5. Why planets orbit instead of flying away. By now, gravity has begun to look very different from the version most of us first learned. It no longer feels like a simple invisible pull reaching across empty space. Space itself turned out not to be truly empty. Mass turned out not to be passive. And falling, perhaps strangest of all, began to look less like something being done to an object and more like the object following the most natural path available to it in a shaped world. And if that is true, then another question rises very quietly from the darkness. Why do planets orbit instead of flying away? Or perhaps, just as importantly, why do they not simply fall straight in? Because if the Sun shapes the spacetime around it, and if Earth is moving through that shaped region, then why does Earth trace that calm, repeating path year after year? Why not drift off into the cold? Why not plunge inward? Why this graceful balance between escape and collapse? This is where the story of gravity becomes less like a drop and more like a dance. A falling apple is easy to picture. It begins with almost no sideways motion, so its path into Earth is direct and quick. But a planet is different. A planet is not merely suspended, waiting to be released. It is already moving, and moving quickly, long before the word orbit enters the conversation. And that speed, that sideways motion, changes everything. In fact, one of the simplest and most beautiful ways to understand an orbit is this. An orbit is what happens when falling and forward motion become inseparable. That sentence may sound almost too simple for something as grand as a planet circling a star, but there is great truth hidden inside it. A planet like Earth is indeed falling toward the Sun. It is just doing so in such a way that it never reaches the Sun directly. It keeps missing, again and again, not by accident, but by the very nature of its motion through curved spacetime. To feel this more clearly, it helps to start somewhere familiar. Imagine throwing a ball across an open field. If you toss it gently, it travels a short distance and drops. If you throw it harder, it travels farther before it falls. Throw it harder still, and farther still. The Earth is curving beneath it the whole time, but over short distances that curvature is too subtle to notice. Now imagine, just as a thought experiment, that you could throw the ball impossibly fast, so fast that as it falls, the ground curves away beneath it at exactly the same rate. The ball would keep falling, but the Earth would keep curving away. The result would be extraordinary. The ball would never hit the ground. It would go all the way around the planet. That is an orbit. Not the absence of falling, but the endless continuation of it. This idea has been around in one form or another for centuries, and it remains one of the most useful bridges between our everyday intuition and the deeper picture. But when we now place it inside the geometry we have been building toward, it becomes even more satisfying. The planet is not merely being pulled inward while trying to escape tangentially. It is following the natural path available to it in a region of spacetime shaped by the Sun's mass. That natural path is curved, and because the planet also has forward motion, the result is a closed or nearly closed path around the Sun. The old picture and the deeper picture overlap here in a beautiful way. The old one says the planet is always falling inward while its sideways speed prevents a collision. The deeper one says the planet moves freely along a geodesic, the straightest available path in curved spacetime. These are not enemies. One is the everyday translation of the other. And that is worth pausing over, because it shows something very lovely about science. Sometimes a new theory does not destroy the old picture entirely. It reveals the deeper structure beneath it. The older language still works in many settings, but now it is supported by a quieter, wider understanding. Let us stay with Earth for a while, because it is always easier to think clearly when we begin from home. Earth moves around the Sun at about 30 kilometers per second. That is an astonishing speed, though it never feels like it to us because everything around us shares in the motion. We, the air, the oceans, the trees, the cities, all move together. There is no rushing wind from Earth's orbit because we are not cutting through space the way a car cuts through air. We are all inside the motion together, carried along as a single world. That speed is not a detail on the side of the story. It is the story. If Earth were somehow suddenly brought to a stop, it would no longer trace its wide, patient path around the Sun. It would begin moving inward, not instantly colliding, perhaps because the real dynamics are more subtle, but it would no longer have the same orbital balance. On the other hand, if Earth moved much faster than it does now, the character of its orbit would change as well. With enough extra speed, it might shift into a more elongated path, or in the extreme, escape the Sun's hold entirely. So an orbit is not just about mass and geometry. It is also about motion already in progress. That is why the word balance appears so often when people talk about orbits. But balance here should not be imagined as a fragile stillness, like a pencil standing upright on its tip. Orbital balance is not static. It is dynamic, alive with motion. It is more like a bicycle staying upright because it is moving, or a dancer keeping balance through continuous adjustment, not through freezing in place. The Earth does not orbit the Sun by sitting in a perfect compromise between two opposite influences. It orbits because the shape of spacetime around the Sun and Earth's forward motion together create a stable pattern of free movement. That is one reason orbits feel so elegant. They are not the result of a planet constantly fighting gravity. They are not like a prisoner forever trying to run away while being dragged back by chains. An orbit is not a struggle in that crude sense. It is a form of belonging to a shaped path. The planet is not resisting the Sun every second. It is participating in the geometry the Sun helps create. This matters because language can quietly shape the emotion of an idea. If we say a planet is trying to fly away, that suggests a kind of conflict that is not really there. If we say it is trapped, that is not quite right either. It is moving freely, but within a curved structure. It is neither fleeing nor imprisoned. It is following. And following, in this context, is a much calmer word. A helpful image, though still imperfect, is to think of a leaf caught in a very broad, gentle whirlpool. Not the violent whirlpool of a storm drain, but something vast and slow, where the motion is almost graceful. The leaf does not need to be yanked from all sides by separate commands. The shape of the motion around it already defines the route it will tend to take. Again, the analogy is limited, because a whirlpool happens in water and an orbit does not happen in any fluid like that, but it captures something important. Motion can be curbed by the structure of the environment without requiring a separate visible hand pushing at every instant. This becomes even clearer when we compare different possible paths. Imagine Earth moving a little slower than it is now. It might trace a path that dips closer to the Sun. Imagine it moving a little faster. The path might widen, change the speed enough, or change the direction at the wrong time, and the orbit becomes more elongated, more oval, perhaps more unstable in relation to other bodies. At a certain threshold, the path no longer closes around the Sun at all. Earth would move onto an escape trajectory, falling outward from the Sun's influence in a very broad sense, though falling outward is itself a little deceptive. What would really happen is that its motion through space-time would no longer be a closed loop around the Sun. So when we ask why planets orbit instead of flying away, the answer is not simply that gravity prevents escape. It is that the actual motion a planet has, combined with the geometry around the star, produces a curved path that remains bound. And when we ask why planets orbit instead of falling straight in, the answer is equally gentle. They already possess sideways motion. They do not begin from rest above the sun the way an apple begins nearly from rest above the ground. Their motion carries them onward while spacetime's curvature carries the path around. This is why orbits are so deeply tied to the history of how a solar system forms. Planets do not usually appear motionless and then get assigned an orbit afterward. They form within rotating disks of gas and dust around young stars. The whole system is already in motion from the beginning. Clouds collapse, spin, flatten, and gradually assemble matter into stars, planets, moons, asteroids. The motions we see later are inherited from that earlier rotating structure. The universe is often generous in this way. It gives us the answer early and then lets us spend centuries understanding it. A newborn solar system is not a collection of objects dropped into stillness. It is an evolving pattern of motion from the very start. And that means an orbit is not some last-minute correction. It is a natural continuation of the story. There is also something deeply reassuring in the predictability of this. Once a planet settles into a stable orbit, the path can remain steady for astonishing spans of time. Not perfectly unchanged, because real solar systems contain many bodies tugging and shaping one another, and no orbit is absolutely eternal. But stable enough that seasons come, years repeat, eclipses can be predicted, and worlds can build histories around the regular return of light. We live inside one of those histories. Our calendar, our agriculture, our sense of the year, the very rhythm of climate and migration and daylight, all quietly depend on Earth's orbit. It is easy to hear the word orbit as something abstract and astronomical, but orbit is also spring returning. It is the slow tilt of sunlight across a hemisphere. It is the lengthening and shortening of days. It is the fact that life on Earth learned the shape of a repeating year because our world keeps tracing the same great path around the sun. In that sense, orbit is not only a physical fact, it is one of the hidden foundations of lived experience. If this slow exploration is helping you settle your thoughts, you can gently support the channel with a like or a quiet subscription. And if you want, you can leave a comment sharing what part of the world you're listening from tonight. There is something peaceful about knowing we are all on the same moving world, tracing the same orbit together, even while sitting still. Now, there is another subtle point here that makes the whole picture even richer. The sun does not simply sit motionless while the planets move around it in perfect circles. That older image, while useful for beginners, is not fully true. In reality, the sun and the planets all move. A planet pulls on the sun too, though much less because of their difference in mass. The Earth does not orbit a perfectly fixed sun in an absolute sense. Both Earth and Sun move around a common center of mass, called a barycenter. For Earth and the Sun, that common center lies very near the Sun's center because the Sun is so much more massive. But in other systems, especially when planets are very massive or very close, the shared motion becomes easier to notice. This detail matters because it reminds us again that gravity is relational. The world is not arranged as absolute still centers and obedient moving objects. It is a web of mutual influence. The larger body shapes more strongly, yes, but nothing exists in total isolation from the rest. The same is true of moons around planets, and even of stars moving within galaxies. Everywhere we look, motion is layered. Things orbit while also being orbited. Paths combine with larger paths. A moon circles a planet while the planet circles a star while the star circles the center of a galaxy while the galaxy moves within a larger cosmic structure. Reality is full of nested dances. And yet, despite that complexity, the underlying principle remains gracefully simple. A stable orbit emerges when forward motion and curved geometry fit together in the right way. This is one reason circular or near-circular orbits feel so satisfying to the mind. They express a kind of continuous agreement between motion and structure. Not a forced compromise, but an enduring fit. Of course, not all orbits are perfect circles. In fact, most are ellipses, at least slightly. Earth's orbit is very close to circular, but still not exact. Some comets have much more elongated paths, spending long periods far from the Sun and then swinging inward dramatically before retreating again into the dark. The shape of an orbit reflects initial conditions, energy, angular momentum, and the influence of other bodies. But whether the orbit is nearly circular or strongly stretched, the same deep idea remains. The object is not randomly wandering. It is tracing one of the paths made possible by the system's geometry and motion. The word angular momentum appears often here, and while it can sound technical, the feeling behind it is not so difficult. It is the tendency of a moving object to keep sweeping around a center unless something changes that motion. You can feel a simple version of it when spinning a weight on a string, or even when turning sharply while riding a bicycle. Motion around a center carries a certain stubbornness with it. That stubbornness is part of why orbits persist. Not because the planet wants to resist the star, but because motion already underway has structure and consequence. The universe does not have to rebuild an orbit from scratch every moment. Once the pattern exists, it continues naturally unless something significant disrupts it. And that is perhaps the most restful thing about orbital motion. It is not a crisis being barely avoided. It is a stable pattern being faithfully repeated. This is easy to forget because gravity is often taught through dramatic language. Pulling, trapping, falling, escaping. Those words are not wrong, but they can make celestial motion feel more violent than it often is. In truth, much of the universe unfolds with a kind of quiet patience. Planets do not scream around stars. Moons do not panic around planets. Their paths are often smooth, measured, and mathematically beautiful. Even the word fall becomes gentler when we understand it properly here. A planet in orbit is indeed falling, but it is a sustained, balanced fall, one that turns continually into travel. It is falling without collapse, falling without impact, falling in such a way that the path becomes a circle or ellipse rather than a descent to the center. That idea can take time to feel natural, because in everyday life a fall usually ends quickly. It ends with a floor, a splash, a collision, a stop. We are used to falls finishing. But in the openness of space, with the right speed and geometry, a fall can continue indefinitely. A fall can become a year. A fall can become geological ages. A fall can become the quiet rhythm around which an entire biosphere organizes its seasons. That is an orbit. And the opposite case, escape, is just as revealing. If an object has enough speed in the right direction, its path no longer remains bound to the star in a closed way. It does not break free in some dramatic cinematic sense. Rather, the curve of its path opens out. The object still moves through the shaped spacetime around the star, but its motion and energy are such that the route does not return. It passes through and continues on. That is why, flying away is not the default opposite of orbit, but one of several possible geometries of motion. In this sense, orbits are not just allowed by gravity. They are expressions of gravity properly understood. If mass shapes the world around it, then curved paths are not an accidental side effect. They are part of what that shaping means. And once you see that, the night sky changes just a little. The moon no longer merely circles Earth out of habit. It is engaged in continuous free motion through curved spacetime. Earth no longer merely loops around the sun because of some invisible leash. It follows a natural path in a region the sun's mass helps define. The planets become less like marbles tied to a central weight and more like participants in a grand geometrical choreography. That word choreography may sound poetic, but it is not misplaced. An orbit really is a kind of dance, because it depends on relation. Speed alone is not enough. Mass alone is not enough. Position alone is not enough. The path emerges from how these all meet. And once established, the dance can continue with astonishing grace. There is even a kind of humility hidden in that grace. Earth's orbit is not special because it is ours, at least not physically. It is one among countless orbital patterns in the universe. Exoplanets circle other stars. Moons circle those planets. Binary stars orbit each other. Galaxies interact in larger gravitational patterns. The same quiet principle repeats on scales so vast the mind almost recoils from them. Again and again, the universe reveals that motion does not always need a shove. Often, it needs only a shaped world and a traveler already in motion. And perhaps that brings us to a deeper calm, because it suggests that stability in the universe is not always about forceful control. Sometimes stability comes from fitting a path well, from moving in a way the surrounding structure can sustain. The planet does not survive by overpowering gravity. It survives, if that is even the right word, by belonging to the geometry it inhabits. There may be a human comfort in that too, though science itself does not need it. To belong to a larger order without losing your motion. To move freely, yet not drift meaninglessly. To follow a path that is not a prison and not a panic, but a coherent unfolding. There is something deeply soothing in that image. The Earth is not clinging to the sun in fear of the void. It is not on the edge of disaster every second. It is moving in a stable way through a shaped cosmos. It is held, yes, but not held like a captured thing. Held like a note inside a melody. Held like a rhythm inside a longer song. And every one of us lives inside that song. Right now, as you listen, the Earth is moving along its orbital path. The sun has not stopped shaping the region around us. The years still take their measure from that immense motion. Day and night have their own separate cause in Earth's rotation, but the deeper cycle of the year belongs to orbit. The great path continues, whether we are working, sleeping, worrying, or resting. A whole world in motion, carrying us around a star with such smooth continuity that it feels like stillness. That may be one of the most remarkable things of all. Vast motion can feel like rest when it is shared completely. And now, naturally, one more question waits for us. If planets orbit stars because they follow natural paths through curved spacetime, then what happens to time itself in these regions? Does gravity shape only motion through space, or does it also shape the rate at which time passes? Does a clock near a massive object behave exactly the same as one far away? This is where gravity becomes even stranger. Because mass does not only change where things go, it changes how time flows around them as well. Part 6. Why time changes near gravity. There is something quietly unsettling about the idea that time might not pass at the same rate everywhere. Most of us grow up with a very simple feeling about time. A second is a second. A minute is a minute. If two clocks are working properly, then they should agree, whether one is in a kitchen, on a mountain, or drifting high above the earth. That assumption feels so natural that it almost disappears. We do not even notice that we are making it. And yet, gravity has been preparing a surprise for us all along. Because mass does not only change where objects go, it changes how time passes nearby as well. That is where gravity becomes deeply strange. Not just physically strange, but emotionally strange too. A bending path through space is already unusual enough. But a slowing or stretching of time itself feels like something from a dream, or from science fiction, or from the sort of idea that sounds poetic until you discover it is measurable. But it is measurable. And if we want to understand gravity properly, we have to follow it here. We have to follow it into time. A gentle way to begin is with something we already know from ordinary life. Not as a scientific fact, but as a feeling. We all know that time does not always feel the same. A long night waiting for news can stretch unbearably. A happy afternoon can vanish almost without a trace. Childhood summers can feel vast. An adult year can disappear with alarming speed. We already live with the sense that time is not always experienced evenly. Now, to be clear, that is psychological time, the time of attention and memory and emotion. What gravity affects is not that kind of time directly, but physical time itself. The time measured by clocks. The time that governs processes in matter, signals in circuits, the ticking of atoms, the unfolding of events. And this is where the universe asks us to slow down and listen carefully. Because the claim is not merely that time feels different near gravity. The claim is that time actually passes differently there. A clock closer to a massive object runs more slowly than a clock farther away. That is not a metaphor, not an illusion, not a trick of perception. It is a feature of reality. The first time you hear this, it can sound almost impossible. How can time, which seems so basic and universal, depend on where you are? How can the presence of a planet or star affect the rate at which moments pass? But in a way, we have already been preparing for this without fully noticing. Space and time stopped being separate earlier in our journey. They became spacetime, a woven structure rather than two independent things. And if mass changes the structure of spacetime, then it should not be too surprising, at least in principle, that both parts of that union are affected. Mass does not merely shape paths through space. It also shapes the flow of time. And once that becomes real in the mind, gravity starts to look less like a local inconvenience and more like a deep property of existence itself. A helpful place to begin is with the Earth, because Earth is close enough to feel ordinary, but powerful enough to reveal the pattern. Imagine two clocks. One is placed at sea level. The other is placed high on a mountain. Both are perfect clocks. Both begin synchronized. If you leave them there long enough and compare them with extreme precision, they will no longer agree exactly. The clock higher up, farther from the bulk of Earth's mass, will have ticked a little more. The one lower down, deeper in Earth's gravitational influence, will have ticked a little less. In other words, time runs a little faster higher up. The difference is tiny near Earth, so tiny that in daily life it means nothing to our senses. But tiny does not mean unreal. And once instruments became precise enough, this difference was measured. That fact alone is astonishing. It means the world is not bathed in one universal time flowing evenly over all things. Time is local. Time depends on where you are in a gravitational landscape. And the stronger the gravity, the stronger the effect. This is why black holes are so famous, even apart from all their other mysteries. Near a black hole, the slowing of time becomes extreme. A clock close to the event horizon, if somehow kept there safely for long enough, would run dramatically more slowly compared with a clock far away. To the outside universe, events near that region would appear stretched, slowed, dimmed, almost suspended. But it is important not to rush there too quickly. The black hole is dramatic, yes, but the principle is already here, quietly present in the world around us. Gravity and time are not separate domains that only meet at the edge of cosmic catastrophe. They are already in conversation on Earth, in satellites, in mountains, in clocks, in the very structure of how our planet relates to the rest of spacetime. And perhaps the most beautiful proof of this is sitting in your pocket or in your hand, your phone. Because the GPS system that helps guide modern life only works properly if scientists account for the fact that time passes differently for satellites than it does on the ground. GPS satellites orbit high above Earth, where gravity is weaker than it is here at the surface. Their clocks run at a different rate. If those differences were ignored, navigation would drift quickly and become useless. The corrections built into the system are not decorative refinements. They are essential. Every time someone uses a map app and finds the correct road, they are depending, quietly and almost unknowingly, on the fact that gravity changes time. That is one of the most elegant things in science. A mind-bending truth about the structure of spacetime becomes part of something as ordinary as finding a cafe, a home, a meeting place. Reality is often like that. Profound underneath, casual on the surface. Now, once we accept that gravity changes time, another question naturally appears. Why? Why should time slow down near mass? The short answer is that this is what the geometry of spacetime around mass is like. But that answer, while true, still feels a little distant. So it helps to approach it gently, through analogy, even if every analogy will be imperfect. Imagine a landscape where movement through time is a little like walking along a path. In most regions, the path is smooth and evenly paced. But near a massive object, the local structure changes. It is as if the route itself becomes deeper, heavier, harder to traverse at the same rate. Not in the sense of effort, exactly, but in the sense that the geometry allows less time to pass locally compared with a region farther away. That image is rough, but it points in the right direction. The presence of mass changes the metric of spacetime, which is a technical way of saying it changes how distances and durations are measured locally. Near mass, the shape of time is altered. And this is where gravity's real secret begins to emerge. Because once time is allowed to vary from place to place, falling starts to look different too. Earlier, we said that an object in free fall is not necessarily being pulled in the crude old sense. It is following the straightest available path through curved spacetime. That already shifted the picture. But now the role of time becomes more important. A region near Earth is not only spatially shaped, it is temporally shaped. Time passes a little more slowly lower down than higher up. That means an object extended through space, even something as simple as an apple, exists in a region where the lower part is slightly deeper in Earth's gravity than the upper part. In a tiny but real sense, different parts of the object live in slightly different rates of time. That may sound too small to matter. But in space-time, small differences can define the path. A very gentle way to picture this is to imagine two wheels connected by an axle, moving together across a surface. If one wheel is forced to turn a tiny bit differently from the other, the whole vehicle begins to curve. Not because someone grabs it from the side, but because the structure of its motion is no longer perfectly symmetrical. In an admittedly loose way, something like that happens in gravity. The difference in how time passes across a region helps determine how the straightest paths through spacetime bend. The result is what we perceive as falling. This is one reason many physicists say, carefully and with good reason, that the deepest part of gravity is not only the curvature of space, but the curvature of time. That is a profound sentence, and it deserves to be approached slowly. We often imagine space bending as the main story, because space is easier to picture. We can draw it, stretch it, distort it in our minds. Time is harder. Time has no obvious shape in ordinary intuition. But gravity's effect on time may be the more revealing part. Near mass, clocks slow. Processes slow. The local unfolding of events slows relative to farther regions. And objects moving freely through such a world trace paths that reflect that hidden structure. This helps explain why Einstein's theory felt so radical and so complete. It did not simply revise a force law. It replaced the old stage entirely. Space was no longer passive. Time was no longer universal. Reality became a fabric whose local shape depends on matter and energy. And what we call gravity became the lived consequence of inhabiting that fabric. There is something deeply calming in that. Once the mind stops resisting it, the universe is not governed by crude invisible pulls crossing dead emptiness. It is governed by structure, by geometry, by the quiet agreement between matter, motion, space, and time. And time, in this agreement, is not a spectator. It participates. If this kind of slow, gentle science helps you settle into the night, feel free to like the video, subscribe to the channel, or leave a comment about where you're listening from. There is something strangely peaceful about these ideas traveling through so many different moments of the same world. Now, there is another way to feel the reality of gravitational time change, and it comes from imagination. Imagine two twins, or simply two identical observers. One remains far from a massive object. The other spends time much closer to it, perhaps near an extremely dense star or in a spacecraft lingering near the edge of a black hole's deep gravitational region, if such a thing could be done safely. When they reunite, they will not agree on how much time has passed for each of them. The one who spent time in stronger gravity will have aged less. Again, not as an illusion, not because of memory, not because of emotional strain, but physically. This idea is often combined in the public imagination with high-speed travel, because both speed and gravity can change time in relativity. But here we are focusing on gravity alone. Stronger gravity means slower local time relative to weaker gravity. So if you could spend a year in a very strong gravitational field and then return, you might find that much more than a year had passed for those farther away. That thought unsettles people because it makes time stop feeling shared. It introduces a kind of loneliness into it, perhaps, or at least a kind of separation. We like to imagine that everyone is moving forward together in the same river of time. Gravity says the river is not uniform. The flow differs from place to place. Even the rate of living depends on where you are. But perhaps there is another way to hear it. Perhaps it means that time is not a hard external ruler imposed equally on all things. Perhaps it means time belongs more intimately to the structure of the world than we assumed. Different regions live it differently. A clock near a planet, a clock on a mountain, a clock in deep space, all are faithful to their own local reality. None is wrong. They are simply embedded in different parts of the gravitational landscape. This is one of the great quiet lessons of relativity. Reality can be consistent without being uniform. Different observers can each be telling the truth from within their own place in the structure. And that has a very particular beauty. Now let us return gently to falling, because this is where part 6 really lives. Earlier, we spoke about objects falling without being pulled. We said that free fall is the natural path through curved spacetime. But once gravitational time dilation enters the story, that path becomes easier to understand. Near Earth, time is a little slower lower down. The local structure of spacetime is such that the straightest path for a freely moving object bends toward the region where time passes more slowly. This does not mean objects seek slow time in any conscious sense. It means the geometry of spacetime is arranged in such a way that free motion takes that form. To us, watching from ordinary human scale, the result is familiar. An apple drops. A ball falls. Rain moves toward the ground. But underneath that simple picture is a world in which time itself is part of the reason. That is why gravity feels deeper now than it did at the beginning of our journey. At first, gravity was a force. Then it became a shaped space. Now it becomes a shaped space-time in which the differing flow of time helps define the most natural paths objects follow. The universe does not merely tell matter where to go. It tells clocks how to tick. And both are part of the same story. This is also why black holes feel so compelling even to people who know very little physics. They are extreme not just because they are massive or dark, but because they reveal the truth of gravity in exaggerated form. Near a black hole, the slowing of time becomes so strong that it almost seems to break common sense. Someone far away would see processes near the horizon slowing dramatically. Light climbing away would be stretched and reddened. Signals would become delayed, weakened, drawn out. In films and fiction, this often becomes a dramatic plot device. But in the real universe, even without cinematic exaggeration, the principle is astonishing enough on its own. Time is not immune to gravity. It is one of gravity's most intimate victims, or perhaps one of its most faithful companions. And this changes the emotional atmosphere of the cosmos. The universe is not only a place where paths curve and objects move. It is a place where different regions live through time differently. A mountain peak and a valley floor do not merely occupy different heights. They inhabit slightly different temporal realities. A satellite and a person on Earth do not merely sit in different locations. They move through time at slightly different rates. These are tiny differences, yes, but tiny truths are still truths. And once known, they are hard to unknow. The earth beneath your feet is not just holding you in place. It is shaping the local passage of time around you. The sun is doing the same on a larger scale for the solar system. The galaxy, in its own way, contributes to the larger architecture still. Everywhere mass gathers, time is affected. Everywhere gravity deepens, clocks are changed. And this means that no clock in the universe is ever just telling time in some abstract neutral sense. Every clock is telling local time. Every clock is reporting from inside a particular gravitational story. That may be one of the most beautiful ways to say it. A clock is not merely a machine. It is a witness to the structure of spacetime where it lives. And so are we. We do not feel these differences directly, at least not on human scales. Our bodies are too immersed in the same local environment for that. But the environment is shaping us all the same. Our chemistry, our cells, our breath, our sleep, our speech, all unfold inside a gravitational field that is doing more than merely keeping us on the ground. It is also setting the local rhythm of physical time. There is something profound in that, and perhaps even comforting, because it suggests that time is not some cold external river sweeping over an indifferent universe. Time is woven into place, into gravity, into matter, into relation. It belongs to the shape of the world, and the world, in turn, is richer and stranger than it first appeared. So when we ask why time changes near gravity, the answer is not merely technical. It is structural. Mass changes space-time, and time is part of spacetime. The closer you are to mass, the more deeply you live inside that change. The stronger the gravity, the slower the local ticking of clocks relative to clocks farther away. This is not a quirk, not a side effect, but part of gravity's essence. And now, naturally, another question waits just ahead. If mass changes time and bends the paths of objects and even light, what happens near truly heavy things? Near neutron stars? Near black holes? What does gravity look like when the shaping becomes extreme, when space-time is bent almost to its breaking point? That is where the quiet strangeness becomes immense. And that is where we go next. Part 7. What happens near very heavy objects? There is a quiet comfort in the gravity of ordinary things. The Earth keeps our feet on the ground. The moon circles us with calm regularity. The sun holds the planets in their patient paths. Even once gravity becomes strange, it is still a strange thing we can live with. It bends motion. It changes time. It shapes the world around us. But here, near Earth, it does so gently enough that life can unfold inside it almost without noticing. But gravity does not remain gentle everywhere. There are places in the universe where mass gathers so densely, so intensely, that the familiar version of gravity gives way to something far more extreme. Places where a spoonful of matter could outweigh a mountain. Places where time slows so dramatically that the difference stops feeling like a subtle correction and starts feeling like a wound in reality. Places where even light, the fastest thing we know, cannot easily escape. And yet, even there, the same underlying story continues. The universe does not invent a new set of rules just because things become dramatic. It takes the same quiet principles we have already been learning, the shaping of space-time, the bending of paths, the slowing of time, and lets them deepen until the results become almost hard to believe. That is what we are exploring now. What happens near very heavy objects? Not just planets or ordinary stars, but the densest things the universe can make. To understand that calmly, it helps to begin with a star's life, because these extreme objects do not usually appear out of nowhere. They are often born from collapse. A normal star, for most of its life, is an argument between two tendencies. On one side, gravity is always trying to pull the star inward. Every bit of mass in the star contributes to that inward shaping. On the other side, the star's core is producing enormous pressure through nuclear fusion. That outward pressure pushes back. As long as those two tendencies remain in balance, the star survives in relative stability. Gravity presses inward. Pressure pushes outward. The star glows, and for millions or billions of years, the balance holds. But eventually, for many stars, the fuel that supports that outward pressure begins to run low. And when that happens, gravity starts winning. The star can no longer fully support itself. The core begins to collapse. The outer layers may be thrown off violently in an explosion, depending on the mass of the star, but the inner region keeps compressing. Matter is forced inward with extraordinary power. And in that collapse, the universe begins to reveal how strange matter and gravity can become when packed tightly enough. If the collapsing core is not too massive, but still massive enough, it may become what we call a white dwarf. That is already an astonishing object. A white dwarf can contain a mass comparable to the Sun squeezed into a size closer to that of Earth. Its matter is unimaginably dense compared with anything in ordinary life. Yet in the larger cosmic hierarchy, a white dwarf is only the beginning of the strange. If the remaining core is heavier still, gravity pushes harder. The collapse does not stop at the white dwarf stage. Instead, the atoms themselves begin to lose their familiar structure. Electrons and protons are crushed together. The matter becomes something more compact, more alien, more difficult to picture with everyday intuition. The result is a neutron star. A neutron star is one of the most astonishing things in the universe because it is at once simple and almost impossible. Simple, because in one sense it is just matter under enormous compression. Impossible, because the result feels like something our ordinary world should not allow. Imagine taking more mass than our sun and squeezing it into a sphere only about the size of a city. Not a country. Not a planet. A city. The details vary, but the basic idea remains extraordinary. Something with the mass of a star becomes small enough to fit inside a region perhaps only 20 kilometers across. That means the density becomes almost beyond language. If you could somehow bring a tiny amount of neutron star matter to Earth, just a teaspoon of it, the mass would be immense, far beyond anything a human body or building could meaningfully compare to. Of course, you could never really bring it here intact. Outside the star's extreme pressure, it would not remain in that form. But the comparison helps the mind feel the scale of what has happened. A star has not just shrunk. It has become a different kind of object entirely. And gravity near such an object is correspondingly intense. The surface of a neutron star is not a place where you would casually drop a pebble and watch it fall in the ordinary sense. The difference in gravity between the top of a body and the bottom, even over a human height, could be enormous. Time would pass more slowly there than far away. Light leaving the surface would be strongly affected by the star's gravity. Space and time would both be deeply shaped. Yet, remarkably, a neutron star is not a black hole. This distinction matters, because it reminds us that the universe can push gravity to astonishing extremes without crossing the final boundary. A neutron star still has a surface, in a certain sense. If you could somehow survive near it, which you could not, there would still be a region you could in principle point to and say, there the star is. Light can still escape from it, though it must struggle more than it would from an ordinary star. The geometry is extreme, but not yet absolute. And neutron stars do more than just sit there. Some spin extraordinarily fast. Some rotate many times per second. Their magnetic fields can be intense beyond ordinary imagination. Some become pulsars, sweeping beams of radiation through space like cosmic lighthouses. If the beam happens to cross Earth's line of sight, we see regular pulses, so steady and precise that they once seemed almost artificial when first discovered. That is one of the things I find most beautiful about the universe. Even in places where matter has been crushed beyond normal comprehension, the result can still become something rhythmical, almost serene. A dead star, compressed into a tiny spinning remnant, sending quiet pulses across the galaxy. If this slow journey into the deeper end of gravity is helping you unwind, you can gently support the channel with a like, a subscription, or a quiet comment sharing where you're listening from tonight. It is always strangely comforting to imagine these ideas drifting out under so many different skies. Now, if the collapsing core is even more massive than a neutron star can support, gravity continues. And this is where the story enters the territory that has captured human imagination more than almost any other object in science: the black hole. Black holes are often talked about as if they are cosmic monsters, hungry mouths tearing through space, swallowing everything nearby like vacuum cleaners. That image is dramatic, but it is not very accurate. A black hole is not dangerous because it has some magical new power to reach farther than a star of the same mass. If our sun were somehow replaced by a black hole with the same mass, the Earth would not suddenly be dragged inward and destroyed. It would continue orbiting much as before, because from a distance the spacetime geometry would reflect the same total mass. That detail is important because it clears away one of the most common confusions. A black hole is not about mass suddenly becoming more massive. It is about mass becoming concentrated so densely that the curvature of spacetime becomes extreme enough to create a boundary beyond which escape, as we normally mean it, no longer occurs. That boundary is called the event horizon. The event horizon is one of the most misunderstood ideas in physics, perhaps because it sounds like a surface, a kind of cosmic wall. But it is not a solid shell floating in space. If a small black hole could somehow be approached, and if tidal forces were not already destroying you, crossing the event horizon would not necessarily feel like passing through a hard barrier. Locally, it may feel surprisingly uneventful in some cases. The event horizon is not a material edge. It is a boundary in space-time, a place beyond which all future directed paths lead inward. That is worth saying again more gently, because it is the heart of the matter. Near a black hole, space-time is shaped so extremely that once you cross the horizon, every path that still counts as forward in time takes you deeper in. Not because a hand grabs you, not because you hit a trapdoor, but because the local structure of reality has become that severe. Outside the horizon, there are still paths that lead away. Light can still escape if emitted from the right place with the right direction. Signals can still climb outward, though increasingly redshifted and weakened as the gravity deepens. But at the horizon, the situation changes. Beyond it, escape is no longer just difficult. It ceases to be part of the available future. This is what makes black holes so philosophically haunting. They are not merely dense objects. They are regions where the structure of possible motion becomes radically altered. The future itself seems to point inward. And because we have already learned that gravity changes time, the black hole becomes even stranger. To a distant observer, something falling toward a black hole appears to slow as it approaches the horizon. Its signals become stretched. Its light reddens and fades. The closer it gets, the more time appears to drag from the outside point of view. In a simplified sense, it seems almost to freeze at the edge. But from the viewpoint of the falling object, the experience is different. Its own clock continues. Its own proper time passes normally. It falls onward. This difference between perspectives is one of the great quiet lessons of relativity. The universe can offer two very different truthful descriptions depending on where the observer lives inside the geometry. That alone is enough to unsettle common sense. It means that time near a black hole is not just slower in the small everyday way we discussed with Earth and satellites. It becomes deeply, dramatically altered. The difference between local time and distant time grows until our ordinary language begins to strain. This is why black holes so often become symbols in stories. They seem to injure our assumptions. They do not merely bend paths. They bend the very relationship between events, clocks, signals, and outcomes. They make the universe feel less like a simple container and more like a flexible, dynamic structure whose deepest behavior can still surprise us. But it is important not to let black holes become too mythical. They are real physical objects, or more carefully, real physical regions described by general relativity and supported by overwhelming astronomical evidence. We infer them through the motion of nearby stars, the radiation from matter heating as it spirals inward, the shadows they cast against glowing surroundings, and perhaps most beautifully, the gravitational waves produced when black holes merge. That last part is especially moving, I think. Two black holes, each already extreme beyond easy comprehension, can orbit one another, drawing closer over immense stretches of time, until at last they merge. In doing so, they shake spacetime itself. Not metaphorically. Literally. They create ripples in the fabric of reality that travel outward at the speed of light. And here on Earth, after those ripples have crossed unimaginable distances, instruments like LIGO can detect them. We have, in that sense, learned to listen to collisions between black holes. The universe has become audible in a new way. And this brings us back to something very important. Even the most extreme objects do not abandon the principles we have been learning. They reveal them more dramatically. A neutron star is what happens when gravity compresses matter into extraordinary density, yet not beyond all return. A black hole is what happens when the shaping of spacetime becomes so severe that all future paths beyond a certain boundary point inward. In both cases, gravity is not a separate invisible tug layered on top of reality. It is the geometry of reality becoming more intense. The stronger the concentration of mass, the deeper the curvature. The deeper the curvature, the stranger the behavior of motion and time. That is the story. It is the same story we have been telling since Earth and apples and orbits, only now the dial has been turned much farther. There is another effect here, one that people often hear about in a dramatic way, and that is tidal gravity. Even on Earth, gravity is not exactly identical at every height. The side of Earth facing the Moon feels the Moon's pull a little differently from the center, and the far side feels it differently again. That difference contributes to tides. Usually, tides are gentle enough to become part of life rather than something catastrophic. But near extremely compact objects, the difference in gravity over a short distance can become enormous. This is what leads to the famous idea sometimes called spaghettification. The word is playful, but the underlying principle is serious. If one part of your body is much closer to a strong gravitational source than another, the nearer part experiences a stronger pull. In ordinary life, the difference is too small to matter. Near a black hole, especially a smaller one, it can become extreme. The result would be intense stretching and compression. But even here, there is subtlety. Near a supermassive black hole, the horizon can be so large that the tidal differences at the horizon itself are not necessarily immediately fatal. The violent stretching may happen farther in. Near a smaller black hole, the same effects can become deadly much earlier. The details depend on the size of the black hole and your distance from it. Again, the universe refuses to be simple, even in its extremes. And perhaps that is part of what makes these objects so compelling. They are not just dramatic. They are precise. Their strangeness is not random. It is lawful. Each strange consequence follows from the same geometry, the same local shaping of spacetime, taken into more extreme territory. That can actually be soothing, in a strange way. The universe does not become irrational at the edge of a black hole. It becomes more exact. It reveals the depth of rules we barely notice in ordinary life. Now, there is another question that often arises in the quiet after hearing about black holes. What is at the center? And the honest answer is that our current understanding becomes uncertain there. General relativity, taken on its own, suggests a singularity, a region where the mathematics points toward infinite density and curvature. But infinities in physics are often signs that a theory has reached the edge of its usefulness, not that nature literally contains simple infinities waiting politely at the center. Most physicists suspect that a more complete theory, likely involving quantum gravity, would change the picture there. But we do not yet have that full answer. So black holes are not only extreme, they are unfinished questions. They mark one of the places where our best understanding of the very large and our best understanding of the very small failed to combine cleanly. They are reminders that even after all we have learned about gravity, the story is not complete. And maybe that incompleteness is part of the beauty too. We have come far enough to understand that gravity bends space, changes time, guides motion, creates orbits, forms neutron stars, and produces black holes. We have come far enough to detect the ripples from distant collisions between these impossible objects. And yet there is still a horizon of ignorance ahead of us, a place where our maps fade. That keeps the universe alive. It keeps science from becoming mere cataloging. It keeps wonder from collapsing into routine. And perhaps that is the right place to end this part. Not with fear of black holes, and not with cartoonish drama, but with a clearer feeling for what very heavy objects really do. They show us gravity without its everyday softness. They reveal how deeply mass can shape the world around it. Near a neutron star, matter becomes almost unrecognizable under pressure, and time and gravity grow fierce. Near a black hole, the structure of spacetime becomes so extreme that beyond a certain point, all futures point inward. These are not separate stories from the one that began with apples and falling bodies. They are the same story, spoken in a louder voice. The same universe that lets rain fall gently through a quiet night also builds stars so dense they become cities of collapsed matter, and regions so curved that even light cannot freely leave. One law, one geometry, a whole range of consequences, from the ordinary to the astonishing. And from here, another beautiful question emerges. If mass can bend space-time so deeply that even light must follow those changes, then what does that mean for light itself? Why should something with no rest mass respond to gravity at all? Why does light bend near stars and galaxies? And how can the universe use mass like a lens? That is where our journey goes next. Because gravity does not only guide falling objects and orbiting worlds, it also quietly bends the path of light across the dark. Part 8: Why light also follows gravity. There is something almost magical about light. It does not feel heavy. It has no weight in the ordinary sense. You cannot hold a beam of sunlight in your hand. It does not seem like the kind of thing gravity should care about. A rock falling to the ground makes intuitive sense. A planet curving around a star begins to make sense once you accept shaped spacetime. But light? Light feels different. It feels too pure, too fast, too untouchable. It seems like the one thing that should move in straight lines no matter what. And yet, the universe quietly tells us otherwise. Light also follows gravity. Not because gravity grabs it the way a hand grabs a thread, and not because light secretly becomes heavy in the old familiar sense, but because light, like everything else, must travel through spacetime. And if spacetime has been shaped by mass, then the path light takes through it can be shaped as well. That is the heart of this part. We are going to move slowly from a very simple question to one of the most beautiful ideas in modern physics. If light has no rest mass, why does gravity affect it at all? Why should a ray of starlight passing near the sun curve? Why can galaxies act like lenses? Why can the universe, in a very real sense, bend its own view of itself? To begin, it helps to remember where we are. We have already let go of the old picture of gravity as merely a pull. We have begun to see gravity as geometry, as the shaping of spacetime by mass and energy. Objects fall not because some invisible hand drags them through emptiness, but because they follow the natural paths available in the local structure of spacetime. Time changes near gravity. Orbits become paths through curvature. Neutron stars and black holes reveal what happens when that shaping becomes extreme. And now light enters the story. At first, there is a temptation to ask the question in the wrong language. We want to ask, what force pulls on light? But that question already belongs to the older picture. In the deeper picture, the better question is this: if light always follows the straightest available path through spacetime, what happens when spacetime itself is curved? The answer is beautifully simple. The path bends. This does not mean light is deciding to turn. It does not mean light is slowing down and falling in the ordinary sense. It means that what counts as a straight path in curved spacetime is not the same as what counts as a straight path in flat spacetime. And because light always follows those local straightest paths, its route appears curved when it passes through a shaped region. That may sound abstract at first, so let us slow it down and make it gentler. Imagine walking across a wide hillside in thick fog. You keep your direction as straight as you can. You do not intentionally turn. But the shape of the ground is not flat, and if someone far above were watching, your path across the hillside might not look like the simple ruler line you imagine. The terrain changes what straight means in practice. Now replace yourself with light, and replace the hillside with spacetime near a massive object. That is closer to the truth. A beam of light passing far from a star moves through a region of spacetime that is only gently shaped, so its path appears nearly straight. But as that same beam passes near a very massive body, such as a star, galaxy, or black hole, the local geometry changes more strongly. The straightest available path through that region is no longer the flat space straight line we are used to imagining. So the beam bends. This idea was one of the most powerful consequences of Einstein's theory, because it offered a direct test. If gravity really was geometry, then light from distant stars passing near the sun should be deflected by a measurable amount. That was a bold claim. It was one thing to say planets and falling objects respond to curved spacetime. It was another to say light itself would do the same. But in 1919, during a solar eclipse, astronomers observed the apparent positions of stars near the sun and found that their light was indeed bent in the way Einstein predicted. That observation made Einstein famous, but more importantly, it changed the human picture of gravity forever. The sun was no longer just something bright and hot around which planets moved. It was also something capable of changing the apparent path of light itself. That is a wonderfully strange thing to realize. When you look at a star in the sky, it is natural to imagine a simple direct line between you and that distant point of light. But in a universe shaped by gravity, the route that light took may have been altered on its way to you. The sky is not always a clean geometric map. It can be subtly, and sometimes dramatically, distorted by mass along the path. This means the universe is not just full of light. It is full of paths for light, and those paths are not always simple. A helpful everyday comparison is an optical lens. A glass lens bends light because light travels at different speeds in different materials, causing the path to change direction. A magnifying glass can bring distant things into clearer view or distort them into larger shapes. In a telescope or camera, carefully shaped glass bends light in controlled ways to produce an image. Gravity can do something similar, though by a different mechanism. A massive object can bend the spacetime around it in such a way that light passing nearby changes direction. No glass is required. No physical transparent lens sits out there in space. The geometry itself acts like the lens. This is why the phrase gravitational lensing exists. A star can do it. A galaxy can do it. A cluster of galaxies can do it. A black hole can do it. And because of that, the universe sometimes creates extraordinary images. A distant galaxy may appear stretched into arcs. A single background object may appear doubled, tripled, or even multiplied into several images around the foreground mass. In some cases, when the alignment is especially neat, the background light can form a ring around the lensing object. These are called Einstein rings, and they are among the most beautiful visual demonstrations of curved spacetime we have ever found. They look almost too elegant to be real, and yet they are not artistic embellishments. They are what light does when it passes through a universe shaped by gravity. If this slow unfolding of the cosmos is helping you rest a little deeper tonight, feel free to like the video, subscribe to the channel, or leave a comment sharing where you're listening from. There is something quietly lovely about imagining these bent paths of light reaching so many different rooms and nights at once. Now, it is worth pausing over a subtle point, because it touches one of the most common misunderstandings. When we say light bends near gravity, we are not saying light stops being light. We are not saying it suddenly becomes heavy in the old Newtonian sense. We are saying that gravity changes the shape of the arena light moves through, and because light always travels along the local structure of that arena, its path changes. That distinction matters, because it keeps the picture unified. Gravity does not need a special rule for rocks, another for planets, another for photons. The same deeper principle holds. Curved space-time gives rise to curved motion. Matter follows those paths. Light follows them too. The details differ because light always moves at the speed it does locally, while massive objects do not, but the underlying structure remains the same. That is one reason Einstein's view felt so powerful once people began to absorb it. It reduced the number of separate mysteries. It did not need one explanation for falling apples and another for bent starlight. Both became expressions of the same geometry. And when a theory does that, when it reveals one hidden order beneath many different phenomena, it acquires a kind of quiet beauty. There is another effect of gravity on light that deepens the story even more. Light does not only bend near mass. It can also be stretched. Earlier, when we talked about gravity changing time, we learned that clocks deeper in a gravitational field run more slowly relative to clocks farther away. Since light is deeply tied to time, because light is a wave and waves have frequency, gravity can change the frequency of light as it climbs out of a gravitational well. In simple terms, light leaving a strong gravitational region loses energy in a way that shows up as a shift toward the red end of the spectrum. Its wavelength becomes longer. This is called gravitational redshift. Again, this is not just a poetic idea. It has been measured. And once more, it reminds us that light is not floating above the story of gravity. It is part of it. If a beam of light begins near the surface of a dense star or climbs away from a black hole's deep gravity, the changing structure of spacetime affects not only its path but also the frequency with which it arrives at a distant observer. Color, in a broad sense, becomes part of the geometry story too. That is breathtaking when you stop and really sit with it. Mass changes time. Time affects light. So the color and energy of light can carry a fingerprint of gravity across the universe. This is why astronomers learn so much from light. They are not simply seeing distant objects. They are reading light that has been shaped by motion, time, gravity, temperature, chemistry, and distance. A beam of light arriving at a telescope is not just a messenger. It is a whole history compressed into motion. And gravity is one of the authors of that history. Gravitational lensing becomes especially powerful because it allows us to detect things we cannot see directly. This is one of the most beautiful uses of the idea, because it turns gravity into a tool of vision. Imagine there is a massive cluster of galaxies between us and an even more distant galaxy behind it. The cluster may bend and magnify the background light, making the far object more visible than it would otherwise be. The cluster becomes a natural telescope built out of spacetime itself. Astronomers actually use this effect. Sometimes a distant galaxy that would be too faint to study directly becomes visible precisely because foreground mass has magnified it. The universe lends us a lens. It bends light, increases brightness along some paths, stretches the image, and allows us to see farther than our instruments alone might have allowed. There is something deeply moving in that. The same gravity that complicates the view also expands it. The same curvature that distorts can reveal. And because gravitational lensing depends on mass, whether or not that mass is bright, it also gives us a way to map invisible matter. A galaxy cluster may bend light more strongly than the visible stars and gas alone can explain. That tells us there is additional mass there, unseen but real in its gravitational influence. Much of what we infer about dark matter comes through effects like these. We do not simply see dark matter with ordinary light. We infer its presence because the universe bends light more strongly than visible matter should allow. So gravity becomes not only an actor in the scene, but a diagnostic tool. It lets us trace hidden structure. It lets us weigh the invisible. It lets us notice what the eye alone would miss. That should change the feeling of the night sky a little. The dark between stars is not just empty blackness. It is full of potential paths for light. The bright objects are not merely shining. They are shaping those paths. And what reaches our eyes is not always what left its source in the same neat direction. Light has traveled through a sculpted reality. It has passed through wells of gravity, around stars, through galaxies, along geodesics in a bent spacetime. What we call seeing is, in a deep sense, receiving the outcome of those journeys. That is why astronomy can be so humbling. Even looking becomes more complicated and more beautiful than it first appeared. A distant quasar may appear in multiple places in the sky, not because there are several quasars, but because one beam of light has taken multiple routes around a gravitational lens. Each route may have a slightly different length and pass through different gravitational conditions. That means the images can even arrive at different times. In some extraordinary cases, astronomers can watch changes in brightness appear in one lensed image, then later in another, because the light took different paths through curved spacetime. Just imagine that for a moment. The universe can show us several copies of the same distant object, and each copy can carry a slightly different timing, a different story of travel, because gravity has split and rerouted the light. The cosmos is not just beautiful. It is intricate, and it remains governed by the same quiet principle again and again. Mass shapes spacetime. Spacetime shapes motion. Light, which we once thought might stand outside gravity's reach, turns out to be just as obedient to the local geometry as anything else. There is an emotional shift that comes with realizing this. At first, gravity may have seemed like a local inconvenience, a reason apples fall and feet stay on the ground. Then it became a cosmic architect, shaping orbits and time. Now it becomes part of sight itself. It enters the act of seeing. It influences what can be seen, how it appears, and even whether we notice hidden matter at all. Gravity is no longer just the keeper of bodies. It becomes one of the sculptors of appearance. This makes black holes even more fascinating. A black hole does not emit light in the usual sense, but the spacetime around it can bend the light from matter nearby or from objects behind it. In some images and simulations, the black hole's presence creates warped rings, twisted arcs, and strange mirrored structures in surrounding light. This is not just artistic imagination. It is what happens when light is forced to take paths through extreme curvature. The view around a black hole becomes almost surreal because space-time there is so deeply distorted. When astronomers produced the first image of the shadow of a black hole, what they revealed was not a photograph of a literal black sphere in the ordinary sense. It was an image of the region where light and geometry combine in such a way that a dark central shadow appears against glowing matter around it. It was, in a very real sense, an image of gravity affecting light. That is one of the reasons it was so powerful. It was not merely evidence for a black hole. It was visual evidence that spacetime near extreme mass shapes the paths of light in exactly the strange ways our theories predicted. This all raises a subtle philosophical feeling too. We often imagine light as the great revealer, the thing that shows us reality. But gravity reminds us that even the revealer is shaped. Even light must submit to the deeper structure of the world. So there is no perfectly detached view. No simple beam floating outside the rules. The act of seeing is itself embedded in the geometry of the cosmos. That does not make truth impossible. It makes truth richer. It means that understanding the universe is not just about collecting light, but learning how that light has been guided, delayed, stretched, bent, and transformed along the way. In that sense, astronomy is an act of patient interpretation, a patient reading of light's long memory. And gravity is one of the languages that memory is written in. If we return to the simpler emotional center of this part, perhaps it is this. Light follows gravity because light follows spacetime. That is the cleanest answer. No extra force is required. No special exception. Once you understand gravity as geometry, the bending of light becomes not a bizarre add-on, but a natural consequence. And that is often how science feels at its best. Something that once seemed impossible becomes inevitable, once the deeper picture is in place. At the beginning of this journey, a lot of things might have sounded like separate mysteries. Why do things fall? Why do planets orbit? Why does time change? Why does light bend? But the more we stay with the deeper structure, the more these become one long story told in different voices. Mass changes spacetime. Curved spacetime defines the available paths. Objects follow them. Light follows them. Time is part of that same curved world. And the universe, from apples to galaxies, begins to feel less like a collection of disconnected facts and more like a coherent pattern. That coherence can be very restful, because it means the world is not arbitrary, even when it is strange. The strangeness is structured. The surprise belongs to order, not chaos. The sun bends starlight because the sun shapes spacetime. A galaxy cluster magnifies background galaxies because its mass reshapes the routes available to light. A black hole distorts the visible world around it because curvature there becomes extreme. And our telescopes, our eyes, our measurements, all depend on learning to read the consequences. There is something almost tender about the idea that gravity can act like a lens. A lens usually helps us see. Gravity, in its own way, can do that too. It can distort, yes. It can also reveal. It can hide and uncover at once. It can make the universe harder to interpret and easier to detect. It complicates the view, but it also deepens it. That is a very adult kind of beauty. Not beauty through simplicity alone, but beauty through deeper structure. And from here, we are ready for one of the final great turns in the story. Because if mass can shape spacetime enough to bend the path of light, and if moving masses can alter the local geometry, then can changes in that geometry travel? Can spacetime itself ripple? Can gravity move outward not just as a static shaping, but as a wave? The answer is yes. And those waves are among the most delicate and astonishing things we have ever detected. That is where we go next. Because gravity does not only bend paths in silence. Sometimes, when the universe moves violently enough, spacetime itself begins to reign. Part 9. Can gravity travel through space? There is a natural way most of us imagine gravity. We imagine it as something stable, something always there, something quiet and unchanging. The Earth holds us. The moon circles us. The planets move around the sun. Gravity feels constant, patient, almost still. Even once it becomes strange, once it bends time and guides light and shapes the paths of stars, it can still feel like a fixed architecture, a deep structure that simply exists in the background while everything else moves within it. But the universe has one more surprise hidden inside gravity. Gravity does not only shape space and time in a static way. It can also move. Or rather, changes in gravity can move. Changes in the structure of spacetime can spread outward. And when they do, the universe does something almost impossible sounding. It ripples. This is one of the most astonishing things modern physics has ever suggested, and one of the most astonishing things modern science has ever confirmed. Spacetime is not merely a passive stage that can be curved once and then left alone. Under the right conditions, it can carry disturbances. It can tremble. It can ring. It can send those disturbances outward across unimaginable distances. Those disturbances are what we call gravitational waves. And the story of gravitational waves is, in some ways, the story of gravity becoming audible. To begin gently, let us remember where we are in the journey. We learned that gravity is not best understood as a simple invisible pull acting across emptiness. Space itself is not empty in the ordinary sense. Mass changes the structure around it. Falling became a path through curved spacetime. Orbits became a kind of continuous free motion through that curvature. Time slowed near mass. Light bent when passing through shaped regions. Black holes and neutron stars showed us what happens when the shaping becomes extreme. Now another question quietly appears. If mass changes spacetime, what happens when mass moves? Not just drifts quietly, but accelerates strongly? What happens when very heavy things orbit each other, collide, or explode? Do they simply change the geometry locally, or does that changing geometry spread outward? The answer, according to Einstein, is that it spreads. And the spreading is not like an object flying through space. It is more like a wrinkle moving through fabric. That comparison is imperfect, like nearly all comparisons in this subject, but it helps the intuition. If spacetime is a dynamic structure, then a major disturbance in one region should not remain forever trapped there. The disturbance can travel outward through spacetime itself. This does not mean spacetime is a substance in the everyday sense. It is not a liquid, not a sheet of rubber, not a gas. But it does mean that the geometry is not rigidly frozen. It can change. And if a change happens violently enough, the change can propagate. That is what a gravitational wave is. A traveling change in the geometry of spacetime. A ripple in the distances and durations that define the world. And that is a very strange sentence, because it means that when a gravitational wave passes through a region, it does not merely travel through space like sound through air. It very slightly changes the structure of space itself as it goes. If a wave passes through you, it does not knock you over like a wind gust. It does not burn you like light from a fire. Instead, it stretches and squeezes distances by a truly tiny amount. One direction becomes ever so slightly longer while the perpendicular direction becomes ever so slightly shorter, and then the pattern reverses as the wave continues on. This is not something human senses can feel. The effect is far too small, but it is real. And the fact that it is real changes the emotional character of the universe. Because it means that the cosmos is not only visible and, in some cases, inferable. It is also responsive. It can shiver. A quiet way to think about this is to imagine a calm pond. You toss in a stone, and ripples spread outward in circles. The ripples are not objects moving across the surface in the ordinary sense. The water itself rises and falls locally while the pattern travels outward. Again, spacetime is not water, and gravitational waves are not pond ripples in a literal sense. But the image helps with one central feeling. A local disturbance can create a traveling pattern that carries information away from the event that caused it. That is exactly what gravitational waves do. When extremely massive objects accelerate, especially in asymmetric ways, they can generate these ripples. And the most powerful sources are not ordinary things. They are some of the most extreme systems in the universe. Black holes orbiting each other. Neutron stars spiraling together. Catastrophic motions involving enormous concentrations of mass. This makes sense if we pause and think of gravity not as a fixed background force, but as geometry itself. If very heavy objects are moving around violently, then the geometry around them is not simply sitting still. It is changing. And those changes do not remain local forever. They propagate outward at the speed of light. That last detail matters. Gravitational waves do not travel instantaneously. They move at a finite speed, and that speed is the same cosmic speed limit we have already seen so many times. This means the universe preserves a kind of causal dignity. Events happen, and their gravitational influence does not inform the cosmos all at once. The news travels. A collision between black holes in a distant galaxy sends out a message. That message crosses space over millions or billions of years. Eventually, if the alignment is kind and the instruments are sensitive enough, that message arrives here. And we can listen. That is perhaps the most remarkable part. For a long time, gravitational waves were only a prediction. Einstein's equations suggested they should exist, but even Einstein himself wavered at times over how to interpret parts of the mathematics. The problem was not only conceptual, it was practical. Even if gravitational waves were real, would they ever be large enough to detect? The changes they produce are unimaginably tiny by human standards. A wave reaching Earth from some colossal event far away might alter distances by less than the width of a proton across several kilometers. That is an absurdly small effect. So small that for decades, gravitational waves seemed almost like a beautiful piece of mathematics that might remain forever beyond human reach. But science has a way of rewarding patience. And patience, in this case, lasted many decades. Before detection finally came, physicists had to think carefully about where the strongest waves should come from. A star quietly sitting alone would not do much. A symmetric explosion might not do enough. But a pair of very massive bodies orbiting one another, drawing closer over time, that was promising. Such a system would continuously churn the local spacetime structure. The faster they circled, the stronger the changing geometry. As they spiraled inward, the waves would become stronger and more rapid. And when they finally merged, the release would be extraordinary. Not extraordinary in the way of fire or visible brightness necessarily, but extraordinary in the distortion of spacetime itself. This is the sort of event gravitational wave detectors were built to hear. If this kind of slow cosmic exploration is helping you settle into the night, feel free to like the video, subscribe to the channel, or leave a quiet comment sharing where you're listening from. There is something very peaceful about imagining ripples from deep space passing through our world while so many different people listen under the same larger universe. Now we come to one of the most beautiful moments in the history of modern science. On September 14, 2015, the LIGO observatories detected a signal. LIGO stands for the Laser Interferometer Gravitational Wave Observatory. There are two main detectors in the United States, placed far apart so that a real gravitational signal could be distinguished from local noise. These detectors are extraordinary instruments, built to measure changes in distance so tiny that even describing them feels surreal. Each detector uses long perpendicular arms, kilometers in length, with laser beams bouncing between mirrors. Under ordinary conditions, the light traveling back and forth is arranged so precisely that tiny differences can be measured through the way the beams interfere with one another. If a gravitational wave passes through, one arm is stretched ever so slightly while the other is squeezed, and then the pattern reverses. The change is minuscule, but in principle detectable. And in 2015, it was detected. The signal came from two black holes that had been orbiting one another far away, gradually losing energy through gravitational radiation, spiraling closer and closer until they finally merged. The event had happened about 1.3 billion years earlier. The ripples from that merger had traveled through the universe for all that time before brushing Earth and gently altering the geometry inside LIGO's arms. That signal is sometimes described as a chirp. And that word, though almost playful, is beautifully accurate. As the two black holes spiraled together, the frequency of the waves increased. The rhythm quickened. The signal rose in pitch and intensity, then ended in the final merger. When translated into sound for human ears, it became a short upward sweep, a cosmic chirp. A tiny sound carrying the memory of two black holes colliding long before multicellular life on Earth had even become what it is now. That is difficult to sit with without feeling at least a little wonder. Because it means human beings built an instrument capable of noticing a disturbance smaller than atoms across kilometers, and from that disturbance, inferred a catastrophe involving black holes in a distant part of the universe more than 1 billion years in the past. It is almost too much for the mind at first. And yet it happened. That first detection did more than confirm Einstein. It opened a new sense. For centuries, astronomy was mostly visual. We looked at light. Visible light, radio waves, X-rays, infrared radiation, all were forms of seeing. But gravitational waves gave us something different. They allowed us to detect the universe not through emitted light, but through motion in the geometry of spacetime itself. We did not see those black holes merge in the ordinary sense. We felt the universe shake. That is why people speak of gravitational wave astronomy as a new way of listening to the cosmos. Not because sound literally traveled through space from the collision to our ears, but because the pattern of the wave carried information in a way more like hearing than seeing. The event announced itself through vibration, and the implications are enormous. Light can be blocked, absorbed, scattered, or never emitted strongly enough in the first place. Black holes, by definition, are not bright in the usual way. But gravitational waves do not care whether an event is luminous. They care about mass, motion, asymmetry, acceleration. They let us detect things that would otherwise remain hidden from ordinary observation. This means the universe became larger the moment we learned to listen to it this way. Events that once would have passed in silence, at least to us, can now leave measurable traces. That changes the feeling of the cosmos. It means that darkness is not quiet in the absolute sense. A region with no visible light may still carry the memory of violent motion. A pair of black holes in total darkness can still sing to the universe through gravitational waves. There is something profoundly beautiful in that idea. It suggests that reality has more channels than the eye alone can read. More ways of speaking, more forms of presence. Now, gravitational waves do not only come from black holes. Neutron stars can create them too, and when neutron stars merge, the story becomes even richer because neutron stars can also emit light and other radiation during the collision. That means scientists can both hear the gravitational signal and see the aftermath through telescopes. When this happened in 2017, it became one of the great scientific events of the century. A gravitational wave signal from two neutron stars merged with electromagnetic observations across many instruments, allowing an extraordinary reconstruction of the event. This kind of multi-messenger astronomy, as it is called, is deeply exciting because it combines different forms of information. Light tells one part of the story. Gravitational waves tell another. Together, they give a fuller picture. And once again, the universe reveals its coherence. Gravity bends light. Light carries information. Moving mass creates waves. Waves carry different information. The same cosmos, many ways of listening. It is easy, when hearing all this, to imagine gravitational waves as rare dramatic fireworks that only matter for exotic events far away. And it is true that the events we currently detect are extraordinary. But the deeper lesson is broader. The universe is dynamic in its geometry. Spacetime is not only something that can be curved, it is something that can be disturbed and can transmit those disturbances. That is a radical truth, because it means the stage is not only shaped. The stage can move. The stage can flex. The stage can ripple in response to violence among the actors. And once you know that, gravity stops feeling like a silent static law and begins to feel more like a living architecture. This also clarifies something about the word wave. A gravitational wave is not a wave of matter thrown out into space like fragments from an explosion. It is not a wind made of particles in the ordinary sense. It is a change in the geometry itself propagating outward. The content of the wave is not stuff moving through a passive arena. The arena is what is oscillating. That can sound almost mystical if phrased too loosely, so it is important to stay grounded. The mathematics describing gravitational waves is precise. The detectors are physical. The signals are real. We are not stepping into metaphor here. We are stepping into one of the deepest literal truths modern physics has revealed. There is something humbling in that. The very thing within which all distances and durations are defined can itself carry patterns of change. And this invites a different emotional response to the sky. On a clear night, the stars may look calm and fixed. But somewhere beyond what we can see, black holes may be spiraling inward. Neutron stars may be colliding. Massive bodies may be shaking the geometry of the cosmos. Those ripples may already be on their way, crossing darkness at the speed of light, indifferent to whether we are paying attention. And every so often, we build something sensitive enough to notice. That is one of the most human things we do. We make ourselves receptive to truths too subtle for the body alone. We extend our senses into the structure of the universe. We listen for the faintest tremor and find a story. And the stories gravitational waves tell are not small. They tell us masses. They tell us distances. They tell us how objects spiraled together. They tell us that black holes are real in the way general relativity described. They tell us that spacetime itself behaves dynamically. They even help test whether the speed of gravity matches the speed of light, which it does to extraordinary precision. Each detection is more than a signal. It is a new piece of confidence in the deeper picture. And perhaps, in a very calm way, it also changes how we imagine silence. Silence in the universe is not absence. A dark sky is not an empty stage. Stillness may contain movement too faint for us to register directly. And far-off violence may pass through us as a whisper in geometry. This is a strangely beautiful thought to take into sleep. That the universe can ring softly enough to escape notice for eons, and yet still be real. That two black holes colliding across 1 billion years can touch the shape of our world, ever so slightly. That a detector on Earth can notice. That the cosmos is not just out there, separate and theatrical, but continuous enough that its deepest events can alter the local distances in a laboratory here. If gravity began for us as a force, it has become by now something far richer. It shapes space. It alters time. It bends light. It creates paths. It forms stars and black holes. And when the universe moves violently enough, gravity itself travels outward as waves in the fabric of spacetime. That is a long way from the old picture of apples falling. And yet it is the same story, deepened. The same hidden order, revealed layer by layer. Which brings us gently to the final step. If gravity is this strange, if it shapes the flow of time, bends the route of light, guides motion, creates black holes, and ripples across the universe, then what does it ultimately tell us about reality itself? What kind of world do we live in if one of its most familiar everyday facts turns out to be geometry, path, distortion, relation, and wave all at once? That is where our journey ends. Not with a formula, but with a wider way of seeing. Because by the time we reach the end, gravity is no longer just about things falling. It becomes one of the clearest windows into what the universe is. Part 10. What gravity tells us about reality. After all of this, after apples and planets and light and time and black holes and waves, it becomes hard to keep thinking of gravity as just one topic among many. It begins to feel more like a doorway into a deeper way of seeing the universe. Because gravity, once you stay with it long enough, stops looking like a simple force that makes things fall. It becomes something much larger than that. It becomes a clue about the nature of reality itself. It tells us that the world is not built the way common sense first suggests. It tells us that space is not empty, that time is not universal, that motion is not always what it seems, that light is not exempt from the deeper structure, and that even the quiet darkness between things can hold shape, relationship, and consequence. That is a lot for one idea to carry. And yet gravity carries it, very calmly. very patiently, as if it had been telling us the truth all along, and we simply needed time to hear it properly. At the beginning of this journey, gravity may have felt familiar in the way a childhood word feels familiar. You know how to use it. You know roughly what it points to. Things fall because of gravity. Planets orbit because of gravity. The moon stays near Earth because of gravity. It sounds complete enough. It sounds finished. But then the deeper questions begin. What is being pulled? Across what? How does the influence travel? Why do all objects fall the same way? Why does time slow near mass? Why does light bend? Why do black holes exist? Why can space-time ripple? And once those questions open, gravity stops feeling like a simple answer and starts feeling like a profound question. That is often how science works at its best. It does not take the mystery away. It takes the shallow certainty away and replaces it with a richer, more structured mystery. The world does not become less beautiful when explained well. It becomes more beautiful, because explanation reveals hidden coherence. And coherence may be one of the most comforting things the universe offers. Because it means that what first looks chaotic is often not chaotic at all. It only appears that way when we are seeing fragments. Gravity has been one of the great teachers of this lesson. It teaches us, first of all, that reality is relational. That may be one of the most important things it tells us. Nothing exists in total isolation. A planet is not merely a thing in itself. A star is not merely a thing in itself. Their mass changes the world around them. Their presence alters paths, alters time, alters light. They are not only objects. They are participants in the shaping of the local universe. This means that what something is cannot always be separated from how it affects the space around it. That is a very deep idea. It suggests that reality is not just made of things, but of relationships. Not just matter, but influence. Not just objects, but geometry. A star is not only a burning sphere. It is also a region-defining presence in space-time. A planet is not only rock and metal. It is also a local shaping of the world around it. Even we, in our small way, are not merely bodies sitting inside space like marbles in a box. We exist within a network of relationships. Gravity touches us not only because we are on Earth, but because Earth, Moon, Sun, galaxy, and space-time itself are all part of one interwoven story. This does not make us less significant. It makes significance harder to isolate, and perhaps more real. Gravity also tells us that reality is geometric in a deeper way than we once imagined. That word, geometric, may sound cold at first. Too mathematical, perhaps. Too abstract. But geometry, at its heart, is simply about shape, relation, path, and structure. It is about how the world is laid out, and what kinds of motion that layout makes natural. Earlier in history, geometry was something we mostly associated with drawings, architecture, measurement, and the tidy certainty of lines and circles. Gravity transformed that idea. It told us that geometry is not only something in the human mind or on a chalkboard. It is woven into reality. The world itself has shape at a deep level, and that shape matters. Things move the way they do because the world is structured the way it is. That idea is subtle, but once it settles in, it changes almost everything. It means the universe is not a stage and then a separate set of actors moving around on it. The stage itself participates. The architecture matters. The structure is not passive. And because time is woven together with space, the geometry is not only about where things are. It is also about when things happen, and how fast time passes in different places. That is a very difficult thing to feel with ordinary human intuition, because our daily life happens in a gravitational environment that is fairly gentle, fairly steady, fairly forgiving. But the universe does not owe itself to our intuition. It only owes itself consistency. And gravity reveals that consistency with remarkable patience. It says that a clock on a mountain and a clock near the ground are not quite living the same physical time. It says that a beam of light passing near a galaxy is not quite following the ruler's straight route we would once have assumed. It says that when enough mass moves violently enough, spacetime itself can ripple. And all of these strange consequences belong not to separate realities, but to one coherent fabric. That coherence matters, because it means the strange parts of the universe are not disconnected exceptions. They are expressions of the same deep order, seen under different conditions. A falling apple and a black hole are not separate worlds. A GPS satellite and a bending beam of starlight are not separate worlds. They belong to one story. And that may be what gravity tells us most powerfully. Reality is deeper than appearance, but not more chaotic than appearance. It is stranger, yes. It is also more elegant. There is another lesson gravity quietly offers, and it may be one of the most humbling. Reality is not built to match the scale of human comfort. That sounds severe when phrased bluntly, but it is not really a harsh statement. It is simply liberating. We often assume that what feels obvious must be fundamental. Flat space feels obvious. A universal present feels obvious. Straight lines seem obvious. The idea that the world is mostly empty feels obvious. The idea that time passes equally for everyone feels obvious. But gravity keeps undermining those assumptions, not cruelly, but firmly. It shows us that the world is not organized around what is easiest for us to imagine. Instead, it invites us to grow, to widen the mind, to let go of pictures that are emotionally convenient but structurally shallow. And in doing so, it gives us something better than convenience. It gives us intimacy with reality. That intimacy has a very particular emotional texture. It can feel destabilizing at first, but if you stay with it gently, it becomes calming. Because underneath the strangeness there is a kind of reliability. The universe is not arbitrary. It does not invent random exceptions. The same mass that helps an apple fall also shifts time. The same geometry that keeps Earth in orbit also bends light from distant stars. The same principles that govern the soft gravity of Earth extend all the way to neutron stars, black holes, and gravitational waves. That kind of continuity is reassuring. It means the universe is not stitched together from unrelated tricks. It is one fabric, one language, many consequences. Gravity also tells us that the universe is more dynamic than the older picture of space ever allowed. The old idea of empty space was, in a way, too still, too dead, too passive, a blank container holding the real things. But gravity says no. Space is not nothing. Spacetime is not inert. It can be curved. It can be stretched. It can carry waves. It can respond to mass and motion. It can participate. That is such a profound shift that it is easy to hear it without quite hearing it. It means the universe is not a pile of objects inside emptiness. It is a structured whole in which emptiness itself is too simple a word. And that thought can change the emotional color of the cosmos. The dark sky no longer feels like a blank void with bright things scattered inside it. It becomes a textured reality. A place where paths exist, where light bends, where time changes, where geometry matters even when nothing visible seems to fill the gap. The darkness becomes less empty and more subtle, less absence and more hidden order. There is something very restful about that, because much of human anxiety comes from the feeling that emptiness means meaninglessness. But gravity suggests that what looks empty may still be structured, still active, still full of consequence. The invisible is not necessarily the unreal. Sometimes it is the deeper layer. If this slow journey through the architecture of the universe has brought you a little calm tonight, feel free to like the video, subscribe, or leave a comment sharing where you're listening from. It is always a quiet pleasure to imagine these ideas settling into so many different nights at once. Another thing gravity tells us is that scale matters, but truth carries across scale. This too is very beautiful. On Earth, gravity feels like weight and falling. In the solar system, it becomes orbit and stability. Near dense stars, it becomes time dilation and fierce curvature. Near black holes, it becomes horizons and the trapping of light. Across the universe, it becomes lensing and waves. The expressions change, the scale changes, the drama changes, but the deeper truth remains. That gives reality a kind of continuity the mind can trust. And trust matters in science, though not blind trust, not emotional surrender. Trust in the sense that deeper understanding should make more of the world fit together, not less. A good theory should connect the ordinary and the extreme. It should let the kitchen floor and the edge of a black hole belong to the same conceptual map. Gravity does that. And in doing so, it tells us something about what good explanations feel like. They do not always make the world smaller. They make it wider while keeping it coherent. That is a rare kind of gift. There is also something deeply human in the fact that gravity led us into all this. Because gravity is one of the first things we ever meet. Long before equations, long before telescopes, long before relativity, gravity is simply there. It is the reason toddlers fall and learn balance. The reason thrown things return. The reason the sky has an up and the ground has a down. One of the first great facts of earthly life. And yet that same familiar fact turned out to be a doorway into the structure of space-time, the bending of light, the slowing of time, the existence of black holes, and the rippling of the universe itself. That should perhaps make us gentler with the ordinary. It is easy to think the extraordinary is always somewhere else. In distant galaxies. In rare events. In unreachable corners of reality. But sometimes the extraordinary is hiding inside the most familiar thing in the room. Sometimes the ordinary only looks ordinary because we have stopped asking it honest questions. Gravity is like that. So is light. So is time. Perhaps that is one of the deepest messages of science for a human life. Not merely that the universe is big, though it is. Not merely that it is strange, though it is. But that the deepest truths are often folded into the things we touch every day. A falling object. A sunrise. A clock. A beam of light. The ground beneath you. Reality is not withholding itself in some distant hidden vault. Much of it is already here, disguised as familiarity. And gravity is one of the greatest disguises of all. There is a final philosophical mood gravity seems to invite, and it is not fear. For something so often associated with weight, gravity can inspire an unexpected lightness of mind. Because once you stop asking the universe to be simple in the way you first imagined, you are freed from defending shallow pictures. You no longer need space to be empty, or time to be the same everywhere, or motion to obey the old everyday story. You become available to a deeper order. And that deeper order is often more beautiful than the simpler one. Not because complexity is automatically beautiful, but because hidden coherence is beautiful. To know that a star changes the shape of the world around it. To know that light must honor that shape. To know that time itself bows near mass. To know that black holes are not merely dark objects, but regions where possible futures narrow inward. To know that the universe can send ripples through space-time from collisions billions of years old. These things do not make the cosmos less intimate. They make it more so. Because they remind us that we are not standing outside reality, looking in as detached spectators. We are embedded in the very structure we are trying to understand. The same gravity that bends galaxies is the gravity that holds our bodies to the Earth. The same time dilation that affects neutron stars already matters, in tiny ways, between satellites and mountains. The same spacetime that ripples under black hole mergers is the spacetime our own lives unfold within. We are not observing from beyond the fabric. We are folds within it. And there is something deeply calming in that realization, especially at night. The universe is not out there, in some absolute sense. It is here too. In the weight of your body. In the path of the moon. In the light reaching your eyes. In the clock near your bed. In the quiet persistence of Earth beneath you. Gravity is one of the ways the cosmos touches everyday life without announcing itself. It is one of the ways the largest scales and the most local moments stay joined. So what does gravity ultimately tell us about reality? It tells us that reality is structured more deeply than appearance suggests. It tells us that space and time are not separate backgrounds but part of one fabric. It tells us that mass and energy shape that fabric. It tells us that motion is often better understood as path than as push. It tells us that light is not outside the order of the world, but inside it. It tells us that time is local, not absolute. It tells us that the universe is dynamic enough for spacetime itself to ripple. And above all, perhaps, it tells us that the world is not made of isolated things floating in emptiness, but of relationships unfolding in a coherent whole. That may be the quiet summary of everything. A coherent whole. Not simple, not always intuitive, but coherent. And perhaps that is enough to rest with tonight. The next time you feel your feet against the floor, you may remember that the sensation is more than just weight. It is a conversation between your body and the curved spacetime around Earth. The next time you look at the moon, you may remember that it is not hanging there by habit, but tracing a path through geometry. The next time you look at starlight, you may remember that its journey may have been bent by invisible structures along the way. The next time you open a map on your phone, you may remember that even this ordinary act depends on gravity changing time. And if you ever feel very small under the night sky, perhaps gravity offers a gentler version of smallness. Not the smallness of being irrelevant, but the smallness of belonging to something vast, ordered, and astonishingly intimate. You are not outside the story. You are a local expression of it. A body on a planet around a star in a galaxy in a larger cosmic web. All of it held together not by crude force alone, but by structure, relation, and the quiet depth of spacetime itself. And in that sense, gravity is not only the reason things fall. It is one of the clearest signs that the universe has shape. One of the clearest signs that reality is deeper than it first appears. One of the clearest signs that what holds us is not merely downward pull, but a hidden architecture vast enough to guide worlds, bend light, slow time, and carry waves across darkness. That is a beautiful thing to remember before sleep. That the world beneath you is not just solid, it is structured. That the sky above you is not just distant, it is connected. That the universe is not empty between its brightest things. It is quietly full of paths. And that gravity, one of the oldest words in our lives, was never only about falling. It was always, secretly, about the shape of reality itself. And perhaps, in the soft dark, there is no better thought to drift off with than that. That you are resting tonight not in a random void, but inside a universe with hidden order. Inside a curved world. Inside a reality that, for all its strangeness, still holds together. Sweet dreams.